There is a moment, if you think about it long enough, when the question changes. At first, it seems straightforward. Point a telescope at something far away, and you see light that left the bext long ago. The farther the object, the older the light. This much is intuitive, but at some point, a different question emerges. Not how far have we looked, but how far can we ever look? Not what have telescopes shown us, but what will they never be able to show, no matter how powerful they become. That second question is harder. It requires thinking not just about technology, but about the universe itself, about limits that are not engineering problems to be solved, but features of reality to be accepted. The moon sits roughly 384,000 kilometers from Earth. Light crosses that distance in about 1.3 seconds. When you look at the moon, you see it as it was just over a second ago. This delay is so small that it feels like the present. For all practical purposes, you are seeing the moon now move outward to the sun. The distance grows to about 150 million kilometers. Light takes approximately 8 minutes and 20 seconds to make that journey. The sun you see is always the sun of 8 minutes past. If the sun suddenly vanished, you would not know for over 8 minutes. You would continue to feel its warmth, see its light, orbit its gravity for that duration before the absence reached you. This is already strange if you sit with it. The present moment, as we experience it, is a construction. Every observation is a report from the past, delayed by the time light needs to travel. But at the scale of the solar system, these delays are still measured in minutes or hours. They are noticeable, but not dramatic. The real strangeness begins when you leave the solar system behind. Proxima Centauri, the nearest star beyond the sun, lies about 424 light-years away. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. When you observe Proxima Centauri, you are seeing light that departed over 4 years ago. If that star exploded tonight, you would not see the explosion until 2029 or beyond. This is not a metaphor. It is not a poetic way of describing distance. It is literal. The photons entering your telescope or your eye originated in the past and have been traveling ever since. They carry information about their source as it existed at the moment of departure. Nothing more recent can reach you until more time passes. Now extend this further. The Andromeda Galaxy, the nearest large galaxy to our own, sits approximately 2.5 million light-years away. The light arriving from Andromeda tonight left when early human ancestors were walking the African plains. No member of our species had yet existed. The galaxy you see is a portrait from deep in the past, frozen into photons that have been crossing intergalactic space ever since. This is the foundation. Distance equals time. Farther means older. Every telescope ever built operates on this principle, whether its builders understood it or not. Galileo, pointing his simple refractor at Jupiter in 1609, was gathering light that had traveled for about 40 minutes. He did not know this. The finite speed of light was not yet established, but the physics worked the same regardless of awareness. So here is the natural thought. If looking farther means looking earlier, then perhaps we can look all the way back. Build a powerful enough telescope, point it at objects far enough away, and see the beginning itself. See the moment everything started. This is where the question quietly transforms. The Hubble Space Telescope, launched in 1990, became the most famous instrument for peering into the distant past. Its observations over 3 decades revealed galaxies billions of light years away, galaxies whose light had been traveling since long before Earth existed. One of its most celebrated images, the Hubble Ultra Deep Field, captured a tiny patch of sky, less than a tenth the diameter of the full moon, and within that patch revealed approximately 10,000 galaxies. These galaxies span a vast range of distances. Some are relatively nearby, a few billion light years. Others are among the most distant objects Hubble could detect, their light having traveled for over 13 billion years. The most distant galaxies in that image appear as faint smudges, their light redshifted and dimmed by the immense journey. Redshift is important here. As light travels through expanding space, its wavelength stretches. Blue light becomes red. Visible light becomes infrared. The farther the source, the greater the stretch. By measuring redshift, astronomers determine how long light has been traveling, and therefore how old the source appears. Hubble could detect galaxies at redshifts up to about 11 or 12. This corresponds to looking back roughly 13 billion years. The universe is 13.8 billion years old. So Hubble was seeing galaxies from when the universe was less than a billion years old. This is extraordinary. 13 billion years of travel, condensed into a faint smudge on a detector. But here is the question that emerges. Why stop there? If Hubble could see 13 billion years back, why not 14 billion? Why not all the way? The James Webb Space Telescope, launched in December 2021, was designed partly to answer this. Webb operates primarily in infrared wavelengths, which allows it to detect light that has redshifted beyond what Hubble could see. Light from the most distant objects, stretched by billions of years of expansion, shifts out of the visible spectrum entirely. Webb's infrared eyes can catch what Hubble's visible light instruments miss. Within its first year of operation, Webb detected galaxies at redshifts exceeding 13. One candidate, designated JADES GS Z140, showed a redshift around 14, placing it roughly 290 million years after the beginning. Others push towards similar or greater distances. These are galaxies from the universe's infancy, structures that formed when the cosmos was less than 300 million years old. This is impressive. But notice something. The improvements are incremental. Hubble saw to about 13 billion years. Webb pushes to perhaps 13.5 billion years. The gains are measured in hundreds of millions of years, not billions. We are approaching something. A limit is becoming visible. What is that limit? Why can we not simply keep building better telescopes and looking earlier and earlier? The answer lies in a specific moment in cosmic history. Not the beginning itself, but a threshold that occurred roughly 380,000 years after the beginning. This threshold has a name, recombination, and it represents the farthest back that any telescope using electromagnetic radiation, meaning light of any wavelength, can ever see. To understand recombination, we need to understand what the early universe was like. In the first moments after the beginning, the universe was extraordinarily hot and dense. Temperatures exceeded billions of degrees. Matter existed as a plasma, a state where electrons are not bound to atomic nuclei. Protons and electrons moved freely, colliding constantly. In a plasma, photons cannot travel far. Every photon is quickly absorbed or scattered by free electrons. The universe was filled with light, but that light could not propagate. It was trapped, bouncing between particles, unable to stream across space. The universe was opaque, luminous but opaque. like the interior of a star, where light exists but takes thousands of years to random walk its way to the surface. As the universe expanded, it cooled. About 380,000 years after the beginning, temperatures dropped to around 3,000 Kelvin. At this point, electrons could finally bind to protons to form neutral hydrogen atoms. Once atoms formed, photons had nothing to scatter off. The universe became transparent. Light was released and began traveling freely through space. This light is still traveling. It fills the universe today. We call it the cosmic microwave background. The cosmic microwave background is not a distant object. It is radiation from a specific moment, released simultaneously from everywhere in the universe, 380,000 years after the beginning. The light that reaches us now is light that has been traveling for nearly 13.8 billion years. Its original temperature was about 3,000 Kelvin. Cosmic expansion has stretched its wavelength by a factor of roughly 1,100. Today, that radiation has a temperature of about 2.7 Kelvin. Its wavelength has shifted from visible light to microwaves. The cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs. They were calibrating a sensitive antenna and found a persistent noise that they could not eliminate. It came from every direction. Eventually, they realized they were detecting the afterglow of the early universe, the radiation released at recombination. This discovery confirmed the Big Bang model. It showed that the universe had evolved from a hot, dense state, and it revealed something profound about observational limits. The cosmic microwave background is not just a signal, it is a wall. Think about what it represents. Before recombination, the universe was opaque. Photons were trapped. No light from before that moment can reach us, because no light could travel before that moment. The cosmic microwave background is the oldest light in the universe. It is not merely the oldest light we have detected. It is the oldest light that exists. It is the first light that could exist as freely traveling radiation. This is a fundamental limit, not a technological one. No telescope, however powerful, can see beyond the cosmic microwave background using electromagnetic radiation. The information is not there to be collected. The universe before recombination did not emit light that could reach us. It was a fog of plasma, scattering every photon before it could escape. Hubble could not see beyond it. Webb cannot see beyond it. The extremely large telescope, with its 39-meter mirror, will not see beyond it. A telescope the size of a planet would not see beyond it. The limit is set by physics, not engineering. This is worth pausing on. We live in an era where technological progress often feels boundless. Build a bigger machine, develop a better sensor, and you can see more, detect more, know more. In many domains, this is true. But the universe imposes constraints that technology cannot circumvent. The opacity of the pre-recombination universe is one such constraint. It is woven into the fabric of cosmic history. It cannot be observed around, only observed up to. So the question of how far back telescopes can really see has a partial answer. They can see back to the cosmic microwave background. They can see light from 380,000 years after the beginning. Before that, they are blind. But 380,000 years is not the beginning. The universe existed before recombination. The first atomic nuclei formed within the first few minutes. The asymmetry between matter and antimatter was established in the first second. Inflation, the hypothesized period of rapid expansion, may have occurred within the first fraction of a second. The ultimate origin, whatever it was, lies at or near time zero. Can we ever observe these earlier epochs? Can any instrument pierce the fog of the early plasma? Not with light. Light is not the only messenger. The universe produces phenomena that do not interact with matter in the same way photons do. Gravitational waves, ripples in the fabric of space-time, pass through matter without being scattered. Neutrinos, nearly massless particles that barely interact with anything, decoupled from the cosmic plasma far earlier than photons did. Gravitational waves offer a tantalizing possibility. If events in the very early universe produced gravitational waves, those waves would have traveled unimpeded through the opaque plasma. They would not have been absorbed or scattered. They could, in principle, carry information from epochs before recombination, perhaps from the first seconds or fractions of a second. Detecting such primordial gravitational waves is extraordinarily difficult. Current detectors like LIGO and Virgo detect waves from relatively recent events, like merging black holes within the past few billion years. The waves from the early universe would be faint, stretched by expansion, and buried in noise. But they may not be impossible to detect. One approach involves the cosmic microwave background itself. Primordial gravitational waves would have left subtle imprints on the polarization patterns of the cosmic microwave background. A specific pattern, called B-mode polarization, would be a signature of these ancient waves. Several experiments are searching for this signal. In 2014, the BICEP-2 experiment announced a detection, but subsequent analysis revealed that dust in our own galaxy had contaminated the result. The search continues. If primordial gravitational waves are detected, they would provide information about the universe from epochs far earlier than the cosmic microwave background. They could offer evidence about cosmic inflation, the hypothesized rapid expansion in the first tiny fraction of a second. This would extend our observational reach backward in time by an enormous factor. Neutrinos offer another window. Neutrinos decoupled from the cosmic plasma about 1 second after the beginning, far earlier than photons. A cosmic neutrino background exists, analogous to the cosmic microwave background, but much older and colder. Its temperature today is estimated at about 1.95 Kelvin. The density of these relic neutrinos is about 330 per cubic centimeter. Detecting these primordial neutrinos is a formidable challenge. Their energy is incredibly low, far below what current neutrino detectors can register. Various proposals exist for detecting them, but none have yet succeeded. If detection becomes possible, it would open a window onto the universe at an age of 1 second, 380,000 times earlier than the cosmic microwave background allows. These alternative messengers, gravitational waves and neutrinos, are the only known paths to observing the universe before recombination. But even they have limits. Gravitational waves from inflation would carry information about that epoch, but inflation itself is hypothesized to have erased information from even earlier times. The rapid expansion would have diluted any pre-inflationary signals to undetectable levels. If inflation occurred, it may have set a second wall, beyond which gravitational waves cannot reveal anything. Neutrinos carry information from 1 second after the beginning, but earlier than that, even neutrinos were in thermal equilibrium with the plasma. Information from the first fraction of a second may not be encoded in the neutrino background in any detectable way. So there is a hierarchy of limits. Electromagnetic radiation shows us the universe from 380,000 years onward. Gravitational waves might extend this to the first second or fraction of a second. Neutrinos might reach to 1 second. Before that, the earliest moments remain hidden. The very beginning, if such a concept even applies, is likely beyond all observational reach. This raises a deeper question. What do we even mean by the beginning? The standard model of cosmology describes the universe's evolution from a tiny fraction of a second onward. Inflation may have occurred before that, and inflation has a beginning of sorts, but it is not clear whether time itself is meaningful at or before that point. Quantum gravity effects may dominate. Space-time itself may have emerged in ways we do not yet understand. The universe may hide its own origin, not because we lack instruments, but because the origin is not a moment in the usual sense. The concepts we use, time, space, before, and after, may break down near the beginning. Observation may be fundamentally impossible, not for technical reasons, but because there is nothing observationally accessible to observe. This is speculative. We do not know what happened at or near time zero. We have theoretical frameworks, like string theory and loop quantum gravity, that attempt to describe conditions at the Planck scale, but none have been experimentally verified. The origin remains a question for theoretical physics, not observational astronomy. So let us return to what we can observe. The cosmic microwave background represents the wall for electromagnetic telescopes. It is the farthest back that any photon-collecting instrument can see. But within this limit, there is still much to explore. The cosmic microwave background itself contains a wealth of information. The fluctuations in its temperature, tiny variations of a few hundred microkelvins from point to point across the sky, encode the seeds of all cosmic structure. These fluctuations were present at recombination, imprinted by density variations in the early plasma. Over billions of years, gravity amplified these seeds into the galaxies and clusters we see today. The Planck satellite, launched in 2009, mapped the cosmic microwave background with unprecedented precision. Its data constrained cosmological parameters with remarkable accuracy. The age of the universe, 13.8 billion years. The composition, about 5% ordinary matter, 27% dark matter, 68% dark energy. The geometry, essentially flat. These values emerge from analyzing the patterns in the cosmic microwave background. This is not seeing earlier. It is extracting more information from the earliest accessible epoch. The cosmic microwave background is a single snapshot at 380,000 years. But that snapshot encodes conditions from earlier times. The fluctuations were seeded during inflation. The overall temperature reflects the expansion history. The abundances of light elements, hydrogen, helium, and traces of lithium, were set during nucleosynthesis in the first few minutes. By studying the cosmic microwave background in ever greater detail, we learn about epochs we cannot directly observe. This is indirect observation, inferring earlier conditions from their effects on later signals. It is powerful, but it is not the same as seeing. Between the cosmic microwave background and the earliest galaxies lies a period called the Dark Ages. For several 100 million years after recombination, the universe contained neutral hydrogen gas, but no luminous sources. No stars had yet formed. No galaxies existed. The universe was transparent, but dark. The first stars ignited somewhere between 100 million and 400 million years after the beginning. These primordial stars, often called population 3 stars, formed from gas containing only hydrogen, helium, and traces of lithium. No heavier elements existed because no stars had yet lived and died to produce them. These first stars are thought to have been massive, perhaps hundreds of times the mass of the Sun. They burned hot and fast, ending their lives in supernova explosions or collapsing directly into black holes. We have not directly observed a population 3 star. They are too distant and too ancient. By the time their light reaches us, it has redshifted far into the infrared and faded to extraordinary faintness. Webb might detect their collective light or the signatures of their deaths, but individual population 3 stars remain beyond reach. What Webb does observe are the earliest galaxies, collections of stars that formed from gas, enriched by the first stellar generations. These galaxies appear at redshifts above 10, corresponding to ages when the universe was a few 100 million years old. They are small, irregular, and intensely star-forming. They represent the first stages of galaxy formation. Observing these earliest galaxies is challenging. They are faint, distant, and embedded in a universe that was still being ionized by their own radiation. The epoch of reionization, when ultraviolet light from early stars and galaxies reionized the neutral hydrogen that had formed at recombination, occurred between about 150 million and 1 billion years after the beginning. During this period, the universe transitioned from mostly neutral to mostly ionized. The details of reionization are still being mapped. Observations of distant quasars, whose spectra show absorption features from intervening neutral hydrogen, help constrain when and how reionization occurred. Webb is contributing by observing galaxies within the epoch of reionization, measuring their properties, and estimating their contribution to the ionizing radiation. All of this occurs within the accessible epoch, after the cosmic microwave background. The wall at 380,000 years remains uncrossed. Every observation of galaxies, quasars, or any other luminous source is an observation of something that happened after recombination. Now let us consider distance rather than time. The cosmic microwave background has a redshift of about 1/100. This means the universe has expanded by a factor of roughly 1,100 since that light was emitted. At the time of emission, the matter that released those photons was about 42 million light-years away from the matter that would eventually become us. Today, that same matter is about 46 billion light-years away. The 46 billion light-year figure is the current distance to the surface of last scattering. It is larger than the age of the universe times the speed of light, which would be about 13.8 billion light-years. This is because space has been expanding while the light was traveling. The matter that emitted the cosmic microwave background has receded during the 13.8 billion years it took for the light to reach us. This is counterintuitive, but correct. The radius of the observable universe is about 46 billion light-years, even though the universe is only 13.8 billion years old. The difference arises from cosmic expansion. Within this radius, everything is in principle observable. Every photon that could reach us has had time to make the journey. Beyond this radius, light has not yet had time to arrive. The observable universe has an edge defined by the cosmic microwave background's current distance. But this edge is not static. The universe continues to expand, and in fact, expansion is accelerating due to dark energy. This means that distant objects are receding from us faster over time. Some objects that are currently visible will eventually cross an event horizon and become permanently unobservable. Their light, still en route, will never arrive because the space between us will stretch faster than the light can traverse it. Over cosmic timescales, the observable universe will shrink. Distant galaxies will fade, their light redshifting to ever longer wavelengths until they disappear from detection. Eventually, only the galaxies gravitationally bound to our local group will remain visible. The rest of the cosmos will be hidden behind an ever closer horizon. Future astronomers, billions of years from now, will see a very different universe. The cosmic microwave background will still exist, but will be colder and fainter. Distant galaxies will have vanished. The evidence for the Big Bang, for the expansion of the universe, for the existence of galaxies beyond the local group, will be largely erased. We live in a privileged epoch, cosmologically speaking. The universe is old enough for galaxies and observers to exist, but young enough for the evidence of cosmic history to remain detectable. This window will not last forever. The observations we make now are part of a limited opportunity. This brings us back to the question, how far back can telescopes really see? The answer has layers. For electromagnetic radiation, the limit is the cosmic microwave background, approximately 380,000 years after the beginning. This limit is fundamental. It arises from the opacity of the early universe and cannot be circumvented by any technology. Within this electromagnetic limit, Webb and future telescopes will observe the earliest galaxies, probe the epoch of reionization, and characterize the dark ages through indirect signatures. They will push toward the wall without crossing it. Beyond electromagnetic radiation, gravitational waves and neutrinos offer potential windows to earlier epochs. Gravitational waves might reveal information from inflation, perhaps from the first fraction of a second. Neutrinos might carry data from 1 second after the beginning. These observations remain in the future, awaiting technological developments that are currently uncertain. Before the first second, the universe becomes increasingly speculative. Theoretical physics offers frameworks for understanding these earliest moments, but observational confirmation is lacking and may be permanently out of reach. The very beginning, whatever form it took, is likely hidden not just by technological limits, but by the structure of physical law itself. So telescopes can see back to 380,000 years with light. They might eventually see back to fractions of a second with gravitational waves. They cannot see the beginning. There is a wall, and beyond it, the universe keeps its earliest secrets. This is not a failure. It is a feature. The universe has a structure, and that structure includes boundaries on what can be known through observation. Recognizing these boundaries is part of understanding the cosmos. What lies beyond the observable horizon? What existed before the cosmic microwave background? What preceded the first second, the first fraction of a second? These questions may never have observational answers. They are not engineering challenges waiting for better instruments. They may be limits inscribed into the universe itself. The most ancient light we can ever receive is already arriving. It has been traveling for 13.8 billion years, cooling and stretching as the universe expanded. It carries information about a cosmos that was opaque until the moment it was released. Before that moment, there's no light to receive. The universe was lit, but the light could not escape. This is the answer to the title question. Telescopes can see back to the moment the universe became transparent. Beyond that, they are fundamentally limited. Different instruments using gravitational waves or neutrinos might extend this reach, but even they have limits. The very beginning, if it is a beginning at all, remains beyond all observational access. The cosmic microwave background fills the sky in every direction. It is the oldest thing we can see. It is the edge of the visible past. And it is there because the universe was once so hot that light could not travel, until one day it could. This realization transforms how we think about observation itself. When we look at the night sky, we are not just looking at distant objects. We are looking at the past, reaching backward through time with every photon we collect. The farthest we can reach is determined not by our instruments, but by the universe's history. There is a surface, a last scattering, a moment when light was freed. Beyond it lies opacity, a fog of plasma that no electromagnetic observation can penetrate. We have come far, from Galileo's simple lenses to orbiting infrared observatories, from measuring the moons of Jupiter to mapping the fluctuations in the primordial glow. Humanity has extended its sight across billions of years and billions of light years. Each generation built on the last. Each instrument revealed what had been hidden. But there is an end to this progression. Not an end to discovery within the accessible universe, which remains vast and rich with mysteries, but an end to the backward reach of time. The cosmic microwave background is that end. For light, other messengers might push the boundary slightly earlier. But the true beginning, the ultimate origin, is likely beyond all observation, hidden not by distance, but by the very nature of what it means to observe. The universe emerged from something we cannot see. It passed through epochs we cannot witness. And then, 380,000 years in, it became transparent. That moment, that transition from opacity to clarity, is the oldest thing our telescopes will ever detect. This is humbling and clarifying. It defines the scope of observational cosmology. It distinguishes what we can learn from data and what we must leave to theory. It reveals that the cosmos, however much we discover, retains an essential mystery at its core. And yet, within the accessible portion, there is enough. Billions of galaxies, trillions of stars, patterns in the ancient light that encode the seeds of everything. A history stretching from just after the beginning to the present moment. The observable universe, bounded as it is, remains an inexhaustible subject for inquiry. Telescopes will continue to improve. Webb will be joined by larger and more sensitive instruments. Ground-based observatories with mirrors tens of meters across will see fainter objects than ever before. Space missions will survey the cosmos at wavelengths we have barely explored. Each advance will reveal new details, new phenomena, new questions, but none will see before the cosmic microwave background. That limit is permanent. It is part of the universe we inhabit, as fundamental as the speed of light or the charge of the electron. Accepting it is not a defeat, but a recognition of reality. The night sky, viewed through any telescope, is a mosaic of moments. Nearby stars show their recent past. Distant galaxies reveal epochs long before Earth existed. The cosmic microwave background, at the edge of detection, shows the universe at the dawn of transparency. Each photon has its own history, its own journey through expanding space, its own message from the past. We are receivers of these messages. Our instruments gather photons that have traveled for nanoseconds or for billions of years. We decode their information, reconstruct their sources, and assemble a picture of cosmic history. The picture is incomplete. It always will be. But it is true, insofar as observation can establish truth. The question was how far back telescopes can really see. The answer is, to the cosmic microwave background, to the moment the universe became transparent, to 380,000 years after whatever began it all. Beyond that, light cannot go. Other signals might reach slightly earlier. The very beginning remains hidden, perhaps forever. This is the limit of telescopic sight. It is not a wall we can break through. It is the edge of what the universe allows us to observe. Within that edge, discovery continues. Beyond it, the cosmos guards its earliest secrets, unreachable by any light. The photons arriving now from the cosmic microwave background have been traveling since before any star existed, before any galaxy formed, before the first atoms bonded into molecules. They are messengers from an alien era, a universe of plasma and radiation, on the verge of becoming the structured cosmos we know. They mark the boundary between what we can see and what we can only imagine. Every telescope, from the smallest backyard refractor to the largest space-based observatory, operates within this boundary. Every observation, from the nearest planet to the most distant galaxy, is bounded by it. The cosmic microwave background is not just a signal to be measured. It is the horizon of electromagnetic observation, the farthest surface we will ever image with photons. And so the question has its answer. Telescopes can see far farther than human intuition can easily grasp. They can see across billions of light years and billions of years. They can capture light from the universe's first billion years of existence. They can map the fluctuations in the primordial glow, but they cannot see the beginning. They cannot see before the universe became transparent. They cannot penetrate the opacity of the first 380,000 years. This is the limit, and it is absolute. The universe offers much to observe. It offers galaxies in their billions, stars in their sextillions, processes and phenomena beyond counting. It offers a history stretching back 13.8 billion years, accessible through the light that travels across space and time. But it also offers a boundary, a wall beyond which observation cannot reach. Understanding this boundary is part of understanding the cosmos. It defines what questions can be answered empirically and what questions require other approaches. It shapes the discipline of observational astronomy. It reminds us that the universe, however much we learn about it, retains depths that light cannot illuminate. Telescopes show us the past. They show us history written in photons. They show us the universe as it was at various epochs, layered according to distance. And at the deepest layer, they show us the cosmic microwave background, the oldest and most distant thing we can see. Beyond that, there is no light to show us anything. The first 380,000 years are hidden behind the fog of primordial plasma. Other messengers might penetrate that fog, reaching back to the first second or earlier. But even they have limits, and the true beginning, if it exists in any conventional sense, remains out of sight. This is how far back telescopes can really see, to the edge of transparency, to the surface of last scattering, to 380,000 years after whatever initiated everything. And there, at that threshold, observation ends and mystery begins. The light from that ancient epoch still arrives, streaming from every direction, carrying information about a cosmos almost unrecognizable compared to the present. It is the oldest light in the universe, and it will remain the oldest light we can ever detect. Beyond it, the universe existed but left no visible trace. Before it, there is nothing for telescopes to see. This is the boundary of the visible past. This is the farthest reach of observation. This is the answer to the question, and in recognizing it, we understand not only what we can learn, but also the shape of what we cannot know. The observable universe has an edge, defined by the cosmic microwave background. Beyond that edge, the universe exists, but cannot be observed with light. The total cosmos may be far larger, perhaps infinite, but we cannot see it. We are confined to a sphere of accessibility, bounded by the light travel time since recombination. Within that sphere, telescopes will continue to explore. The coming decades will bring new instruments, new surveys, new discoveries. The extremely large telescope will see fainter and more distant objects than any ground-based observatory before it. Future space missions will probe wavelengths and phenomena we have barely begun to explore. The catalog of known galaxies will grow, as will our understanding of their formation and evolution. But no future instrument will see before the cosmic microwave background. That limit is set by physics, not engineering. It is part of the universe's structure, as immutable as the laws that govern particle physics or gravitation. The universe shows us much and hides something. What it shows is vast beyond comprehension, a history of 13.8 billion years, accessible through the light that still arrives. What it hides is the first 380,000 years, cloaked in the opacity of the primordial plasma. This division between the visible and the hidden is not arbitrary. It arose from the evolution of the universe itself, from the moment when neutral atoms formed and light was released. That moment is the origin of the oldest light we can see. Everything before it is electromagnetically invisible, accessible only through theory and through other messengers whose signals are faint and uncertain. The question of how far back telescopes can really see thus has a definite answer. They can see to recombination, to 380,000 years after the beginning. The cosmic microwave background is the farthest and oldest thing they can detect. Beyond it lies opacity, a wall of plasma that scattered every photon before it could escape. Other observations might extend our reach. Gravitational waves from inflation could carry information from fractions of a second after the beginning. Primordial neutrinos could reveal the universe at 1 second. These prospects are exciting but uncertain. Detection remains unachieved. And before the first second, the universe becomes increasingly alien to our concepts. Time and space may not have their usual meanings. The origin, whatever it was, may not be observable in any conventional sense. This is the structure of cosmic observation. The electromagnetic universe has a visible history stretching from 380,000 years to now. Within that history, much is known and more is being discovered. Beyond it lies a hidden epoch, 380,000 years of opacity, followed by the true beginning, which may be fundamentally inaccessible. Telescopes have brought us to the edge of this hidden epoch. They have shown us the cosmic microwave background and mapped its properties. They have detected galaxies at redshifts exceeding 13, only a few 100 million years after recombination. They have traced the evolution of the universe from near its beginning to the present. But they cannot cross the threshold. The cosmic microwave background is the limit. Beyond it, electromagnetic observation is impossible. This is the answer to the question: how far back can telescopes really see? To 380,000 years after the beginning, to the moment the universe became transparent, to the cosmic microwave background, the oldest light in existence. Beyond that, there is no light to see. The universe existed, events occurred, conditions were established that would lead to everything that followed. But those events left no visible trace. They are hidden behind the fog of the early plasma, accessible only through inference, theory, or messengers other than light. This is the boundary of observation. It is permanent, fundamental, written into the physics of the early universe. Recognizing it is part of understanding the cosmos. And within this boundary, the universe offers more than we can ever fully explore. Galaxies without number, histories beyond counting, phenomena that continue to surprise and challenge us. The accessible universe is enough. It is vast, ancient, and endlessly rich. Telescopes will continue to reveal its secrets for as long as there are observers to build them and ask questions about what lies above. The cosmic microwave background marks the edge of what they can reveal. Beyond that edge, the universe keeps its earliest secrets, hidden in the opacity of an era before light could travel freely. This is the limit of how far back telescopes can really see. It is not a limit of technology or imagination. It is a limit of the universe itself. The photons arriving now from that ancient era began their journey when the cosmos was 380,000 years old. They have been traveling ever since, cooling and stretching as space expanded. They carry information about a universe that was about to become transparent, about to release the light that would eventually reach our instruments. Before that release, there is nothing for telescopes to detect. The universe was there, but its light was trapped. Only when recombination occurred, when electrons joined protons to form neutral atoms, could photons begin their journey across cosmic space. This is the moment that defines the observable past. Everything we can see with electromagnetic radiation dates from after this moment. Everything before it is hidden, invisible, electromagnetically inaccessible. The question has its answer. Telescopes can see 13.8 billion years into the past, minus the 380,000 years before recombination. They can see light from the edge of the dark ages, from the first galaxies, from the cosmic microwave background itself. They cannot see the first 380,000 years. They cannot see the beginning. This is how far back telescopes can really see. To the surface of last scattering, to the cosmic microwave background, to 380,000 years after everything started. And there, at that ancient threshold, observation ends. What began before that? What happened in those first 380,000 years? What initiated everything? These are questions that telescopes cannot answer. Other methods might help. Gravitational waves might carry signals from earlier epochs. Neutrinos might encode information from the first second. Theoretical physics might describe conditions we cannot observe. But telescopes, instruments that collect electromagnetic radiation, have a fundamental limit. The cosmic microwave background is that limit. It is the farthest and oldest signal they can detect, the boundary of visible history, the edge of the observable past. Within that boundary, the universe lies open to exploration. Beyond it, mystery remains. This is the structure of cosmic observation, determined not by our instruments, but by the universe's own history. The cosmic microwave background glows faintly in every direction, a remnant of the moment the universe became transparent. It is the oldest light we can see. It is the limit of how far back telescopes can really see. And it reminds us that the cosmos, vast as it is, contains depths that no observation can reach. There is a peculiar kind of clarity that comes from understanding limits. Not the frustration of being blocked, but the precision of knowing where the boundaries lie. The cosmic microwave background is such a boundary. It is not a barrier erected by nature to frustrate us, but a consequence of how the universe evolved. It emerged from physics, from the transition between opacity and transparency, from the moment when electrons and protons combined into neutral atoms. This transition was not instantaneous. Recombination occurred over a period of roughly 100,000 years. A gradual shift rather than a sudden switch. The cosmic microwave background is sometimes called the surface of last scattering because it represents the epoch when photons last interacted significantly with matter before traveling freely through space. But this surface has some thickness, some spread in time and space. The photons we receive today from the cosmic microwave background did not all depart at exactly the same moment. Some left slightly earlier, some slightly later. This blurring limits the sharpness of the information we can extract. The fluctuations in the cosmic microwave background are slightly smoothed by this thickness. Despite this, the information content is enormous. The temperature variations, the polarization patterns, the statistical properties of the fluctuations, all encode data about the early universe. From these patterns, cosmologists have derived the age, composition, and geometry of the cosmos with remarkable precision. This is the nature of observational cosmology. It does not give us direct images of the past in the way that looking at the moon gives us an image of the moon. It gives us signals that must be decoded, patterns that must be interpreted. The cosmic microwave background is the richest such signal from the earliest accessible epoch. The decoding has been remarkably successful. The standard cosmological model, often called lambda CDM for its inclusion of dark energy, lambda, in cold dark matter, CDM, explains the observed patterns with high accuracy. The model describes a universe that began in a hot, dense state and expanded and cooled over 13.8 billion years. It predicts the cosmic microwave background's temperature, its fluctuations, and the distribution of galaxies that emerged from those fluctuations. But the model also has mysteries. Dark matter, which makes up about 27% of the universe's energy content, has never been directly detected. Its presence is inferred from gravitational effects on visible matter. Dark energy, which comprises about 68%, is even more mysterious. It causes the expansion of the universe to accelerate, but its nature is unknown. These mysteries lie within the accessible universe. They concern phenomena that occur after recombination, within the epoch that telescopes can observe. Solving them will require new observations and new theoretical insights, but they are, in principle, solvable through observation. The mysteries of the first 380,000 years are different. They concern epochs that electromagnetic observation cannot reach. They must be approached through other means, through alternative messengers like gravitational waves, through indirect inferences from later observables, or through theoretical frameworks that extend beyond current experimental confirmation. Inflation is the most prominent such framework. It proposes that the universe underwent a period of exponentially rapid expansion in the first fraction of a second, growing from a subatomic scale to cosmic dimensions almost instantaneously. Inflation explains several puzzles about the observed universe, including its overall flatness and the uniformity of the cosmic microwave background across the sky. If inflation occurred, it would have generated gravitational waves that propagated through the opaque plasma and left subtle imprints on the cosmic microwave background's polarization. Detecting these imprints would provide evidence for inflation and constrain its properties. The search continues, with experiments like BICEP Array and the Simons Observatory, designed to measure polarization with extreme sensitivity. But even if primordial gravitational waves are detected, they will reveal only conditions during inflation, not before it. Inflation itself may have erased information about any pre-inflationary state. The rapid expansion would have diluted any pre-existing structures or signals to undetectable levels. This is a kind of cosmic censorship. Whatever existed before inflation, if inflation occurred, has been stretched beyond recognition. The first moments may be fundamentally unknowable, not because we lack instruments, but because the physics of inflation has hidden them. Whether this is truly the case depends on details that are still uncertain. Different models of inflation make different predictions. Some leave more information about pre-inflationary conditions than others. The search for primordial gravitational waves will help distinguish among these models, narrowing the possibilities. But even in the most optimistic scenarios, there are likely to be limits. The very earliest moments, the Planck epoch when quantum gravity effects are expected to dominate, may lie beyond all observational reach. At the Planck time, about 10 to the minus 43 seconds after the beginning, our current physical theories break down. Space and time themselves may have behaved in ways we do not understand. This is the deepest limit. Not just an observational limit, but a conceptual one. The very notions of before and after, of cause and effect, may not apply at the Planck scale. Asking what happened before the beginning may be a question that has no answer, not because the answer is hidden, but because the question is ill-formed. These speculative depths lie far beyond what any telescope can address. They are the domain of theoretical physics and philosophy, not observational astronomy. But they form the backdrop against which the question of telescopic limits is asked. How far back can telescopes really see? The answer for electromagnetic telescopes is 380,000 years after the beginning. For gravitational wave observatories, if they detect primordial signals, perhaps fractions of a second. For neutrino detectors, if they achieve the necessary sensitivity, perhaps 1 second. Beyond these, the universe becomes progressively more speculative. Inflation may have occurred, but is not yet confirmed. The Planck epoch certainly existed, but is beyond current physical understanding. The ultimate origin, if it is an origin at all, is unknown and may be unknowable. This hierarchy of limits shapes our understanding of the cosmos. The electromagnetic universe, accessible to telescopes, extends from now back to recombination. The gravitational wave universe, if accessible, might extend to the first second or earlier. The neutrino universe, similarly, might reach to 1 second. Before that, theory must suffice. Not because we lack the will to observe, but because the signals may not exist, may have been erased, or may require concepts we do not yet possess. The cosmic microwave background is the most ancient signal we receive. It is the foundation of observational cosmology. It is the wall beyond which electromagnetic astronomy cannot reach. and it is beautiful in its implications. The universe was once a plasma. It was once opaque. It released the light that became the cosmic microwave background, and that light has been traveling ever since. Every photon in that radiation began its journey when the universe was 380,000 years old. Every photon carries information about that moment, about the temperature and density variations that would eventually become galaxies. These photons fill the sky. They come from every direction. They are the most numerous photons in the universe, outnumbering all the photons from all the stars and galaxies combined. About 400 photons per cubic centimeter, on average, pervade the cosmos. When you look at the static on an old analog television, a small fraction of that noise comes from the cosmic microwave background. Photons from the dawn of transparency, 13.8 billion years old, contribute to the randomness on the screen. This is how pervasive the signal is. These ancient photons are the limit of how far back telescopes can really see. They are the edge of the observable past. They are the beginning of accessible history. Before them, there is no accessible history. Before them, the universe existed, but left no visible trace. Before them, only theory and alternative messengers might reveal what happened. This is the answer. The answer involves physics and cosmology, history and technology. It involves the evolution of the early universe, the transition from plasma to atoms, the release of light that had been trapped. It involves the speed of light, the expansion of space, the cooling of the cosmos over billions of years, and it involves acceptance. Acceptance that some things cannot be observed. Acceptance that the universe has boundaries on what it reveals. Acceptance that the beginning, the ultimate origin, may lie forever beyond our sight. Within these boundaries, discovery continues. The universe offers more than we can ever fully explore. Every observation, from the moon to the most distant galaxy, is a glimpse into the past. Every photon is a messenger. Every telescope is an instrument for reading history. The cosmic microwave background is the deepest chapter of that history that we can read with light. It is the oldest message we can receive. It is the limit of how far back telescopes can really see. And so the question is answered. The limit is 380,000 years after the beginning. The limit is the cosmic microwave background. The limit is the moment the universe became transparent. Beyond that, there is no light to guide us. Beyond that, we must rely on other methods, other messengers, or accept that some mysteries may never be solved. But within that limit, the universe spreads before us, ancient and vast, inviting exploration. Telescopes have shown us galaxies at the edge of the dark ages, the seeds of structure in the primordial glow, the expansion of space over cosmic time. They have revealed a universe far larger and older than any generation before us imagined. And they have revealed their own limit. The cosmic microwave background is that limit, the farthest back they can see, the boundary of visible history. This is how far back telescopes can really see. And in knowing this, we understand something not just about our instruments, but about the universe itself. A cosmos that emerged from hiddenness 380,000 years in, that released its light and became observable, that offers its history to those who build instruments to receive it. The history is long, and the visible portion is vast, but it has an edge. The edge is the cosmic microwave background. And beyond that edge, the universe guards its earliest secrets, unreachable by any light we can collect. The distance to the cosmic microwave background measured in today's coordinates, is approximately 46 billion light-years. This number is larger than the age of the universe, multiplied by the speed of light, which would be about 13.8 billion light-years. The difference arises because space has expanded during the light's journey. When the cosmic microwave background photons departed, the matter that emitted them was about 42 million light-years away from what would become us. Since then, that matter has been carried by cosmic expansion to its current distance of 46 billion light-years. This is the comoving distance, the distance measured in present-day coordinates. The observable universe is a sphere with this radius, centered on our location. Within this sphere, light has had time to reach us since recombination. Beyond this sphere, light has not yet arrived. The sphere is not centered on anything special. Every observer, anywhere in the universe, has their own observable sphere centered on their own location. If intelligent beings exist in a galaxy 40 billion light-years from us, they have their own observable universe. It overlaps substantially with ours, but includes regions we cannot see and excludes regions we can. There is no privileged position. Every location is the center of its own observational horizon. This horizon is shrinking in a certain sense. Due to the accelerating expansion of the universe, distant galaxies are receding faster than ever. Some galaxies currently visible will eventually cross an event horizon and disappear from view. Their light, still traveling toward us, will be stretched to infinite wavelength and never arrive. Over billions of years, the observable universe will contain fewer and fewer galaxies. The cosmic microwave background will cool further, its wavelengths stretching to centimeters, meters, and beyond. The evidence for cosmic history will fade. This is the far future, beyond any timescale relevant to humanity. But it illustrates the dynamic nature of observation. The universe's accessibility is not static. It changes over time, shaped by the expansion of space. In the very distant future, hypothetical observers would see a very different cosmos. The cosmic microwave background might be too faint and cold to detect. Distant galaxies would have vanished. The evidence for the Big Bang, for the early universe, for the cosmic microwave background might be erased. We live in an era when the evidence is rich. The cosmic microwave background is detectable. Distant galaxies are visible. The expansion history can be measured. The cosmic record is open to us in a way that it may not be open to future observers. This is not a call to urgency, but a recognition of our cosmological moment. The observations we make now are possible because of when we exist, not just what we have built. The universe has a history of revelation, and we are in a phase of that history when much is revealed. The cosmic microwave background is the most ancient part of that revelation. It is the foundation of modern cosmology, the oldest signal we can detect, the limit of how far back telescopes can see, and it carries the imprints of even earlier times. The fluctuations in its temperature reflect density variations that were seeded during inflation. The abundances of light elements were set during nucleosynthesis. The overall temperature reflects the expansion history from the first second onward. By studying the cosmic microwave background in ever greater detail, we learn about epochs we cannot directly observe. The signal is a palimpsest, layers of information from different eras imprinted on the same radiation. Extracting this information requires sophisticated analysis, but rewards us with knowledge of conditions far earlier than the signal itself. This is the power of indirect observation. We cannot see inflation. We cannot see nucleosynthesis. We cannot see the first second, but we can see their effects on later observables. And from those effects, we can infer what happened. The inferences are not as certain as direct observation. They depend on models, on assumptions, on the consistency of multiple lines of evidence. But they have been remarkably successful. The standard cosmological model, constrained by observations of the cosmic microwave background and other data, accounts for the universe's structure and history with impressive accuracy. The model is not complete. Dark matter and dark energy remain unexplained. The nature of inflation, if it occurred, is uncertain. The ultimate origin is unknown, but the broad outline is established. A universe that began hot and dense, expanded and cooled, became transparent at 380,000 years, formed stars and galaxies over billions of years, and continues to expand at an accelerating rate today. This outline emerges from observations. It is not speculation, but science, grounded in data from multiple independent sources. The cosmic microwave background is the oldest and in some ways the most important of these sources, and it is the limit of electromagnetic observation, the limit of telescopic sight, the limit of how far back we can directly observe with light. Gravitational waves and neutrinos may extend this limit. They may reveal earlier epochs, conditions from the first second or earlier. But even they have limits, and the very earliest moments remain beyond any observational method we currently possess. The question of how far back telescopes can really see thus has a definite answer for electromagnetic telescopes. 380,000 years after the beginning. This is the cosmic microwave background, the surface of a last scattering, the moment the universe became transparent. Before that, the universe was opaque. Photons could not travel. The information that light might carry was scrambled by countless scatterings. No electromagnetic observation can penetrate that opacity. This is the answer. It is precise, it is physical, and it is permanent. No future telescope will see earlier with light. The limit is set by the universe, not by technology. Within this limit, telescopes have revealed wonders, galaxies by the billions, spanning billions of years of cosmic history. The cosmic microwave background, ancient and pervasive, carrying the imprints of the early universe, the expansion of space, the acceleration of that expansion, the structure of matter and energy that shapes the cosmos. Beyond this limit, there is no light to reveal anything. The universe existed, events occurred, but no photon survives from before recombination. The first 380,000 years are electromagnetically invisible. This is how far back telescopes can really see, to the edge of transparency, to the cosmic microwave background, to the moment when light was first freed to travel across the cosmos. That moment is now 13.8 billion years in the past. The light from that moment has been traveling ever since, cooling and stretching as space expanded. When it reaches our instruments, it carries information about a universe on the verge of becoming transparent, about fluctuations that would become galaxies, about conditions that would shape everything that followed. This is the oldest information we can receive with telescopes. This is the limit of our backward gaze. This is the edge of the visible past. The universe beyond that edge exists, but cannot be observed with light. It is the hidden past. The 380,000 years before recombination, the first moments of cosmic history. Theory can describe it. Alternative messengers might reveal fragments of it. But telescopes, instruments of light, are forever barred from it. This is the structure of the observable universe, a visible history stretching from 380,000 years to now, a hidden prehistory, inaccessible to electromagnetic observation. A boundary between them, the cosmic microwave background, the oldest and farthest signal we can detect. The question has its answer. The answer is precise and physical. The answer is 380,000 years after the beginning. The answer is the cosmic microwave background. The answer is the limit of transparency. And within that answer, there is enough to explore for generations, enough to reveal the history of galaxies and stars, enough to understand the expansion of space and the growth of structure, enough to place ourselves in the cosmic story. The limit defines the territory. Within the territory, the exploration continues. The telescopes of the future will map this territory in ever greater detail, discovering new objects and phenomena, refining our understanding of cosmic history. But they will not cross the limit. The limit is fundamental. The cosmic microwave background is the boundary. Before it lies opacity. Before opacity lies the beginning, hidden from all electromagnetic sight. This is how far back telescopes can really see. The Planck satellite's final data release in 2018 represented the culmination of decades of effort to map the cosmic microwave background. The temperature anisotropies were measured to precisions of microkelvins. The polarization patterns were characterized across the sky. The data were analyzed with statistical techniques that extracted information about cosmological parameters with uncertainties of 1% or less. From this data emerged the parameters that define our universe. The Hubble constant, the rate of cosmic expansion, was measured at approximately 67 kilometers per second per megaparsec. The density of matter was determined. The density of dark energy was constrained. The age of the universe was calculated. The geometry was found to be flat to within observable precision. These numbers are not abstractions. They describe the cosmos we inhabit. They determine how galaxies cluster, how light bends around massive objects, how the universe will evolve in the future. The cosmic microwave background is the key to these measurements. Its fluctuations encode information about the early universe's composition and geometry. The angular scales of the fluctuations reveal whether space is curved or flat. The relative amplitudes at different scales constrain the proportions of matter and radiation. The overall temperature determines the age and expansion history. No other observation provides such precise information about the early universe. Distant galaxies and quasars offer data points at specific epochs, but they cannot match the statistical power of the cosmic microwave background, which provides information from the entire sky at a single, well-defined epoch. This is why the cosmic microwave background is central to cosmology. It is not just one signal among many. It is the signal, the foundation on which the modern understanding of the universe rests. And it is the limit of how far back we can observe with light, the limit of electromagnetic cosmology. Future observations of the cosmic microwave background will continue to refine our understanding. Ground-based experiments are mapping polarization with greater precision than space-based missions can achieve. These measurements seek the faint signature of primordial gravitational waves, the B-mode polarization that would confirm inflation. If this signature is detected, it will extend our knowledge to epochs far earlier than 380,000 years. Inflation is thought to have occurred within the first tiny fraction of a second. Gravitational waves from that epoch, imprinted on the cosmic microwave background's polarization, would carry information from that ancient time. But even this would not be direct observation of the inflationary epoch. It would be indirect, an imprint on later radiation, requiring interpretation through theoretical models. The cosmic microwave background would remain the directly observed signal, with inferences about earlier times extracted from its properties. The hierarchy of observation remains. Direct observation of the cosmic microwave background at 380,000 years. Indirect inferences about inflation, perhaps at 10 to the minus 36 seconds. Theoretical frameworks for even earlier times, the Planck epoch at 10 to the minus 43 seconds. Each level is less certain than the last. The cosmic microwave background is measured. Inflation is inferred, but not confirmed. The Planck epoch is purely theoretical, beyond any current experimental test. This is the structure of our knowledge. Firm at the foundation, becoming progressively more speculative at earlier epochs. The cosmic microwave background anchors everything. The most ancient directly observed signal, the starting point for all inferences about earlier times. Telescopes have brought us to this foundation. They have mapped the cosmic microwave background and extracted its information. They have detected galaxies at the edge of the dark ages. They have traced the universe's expansion over cosmic time, and they have encountered the limit. The cosmic microwave background is that limit, the farthest back that electromagnetic observation can reach, the boundary of the visible past. The question of how far back telescopes can really see is answered by this limit. The answer is 380,000 years after the beginning. The answer is the cosmic microwave background. The answer is the moment the universe became transparent. Before that moment, light could not travel. Before that moment, no electromagnetic signal could propagate. Before that moment, the universe existed but left no visible record. This is the edge of what telescopes can reveal. Within this edge, the cosmos lies open to exploration. Beyond it, the first 380,000 years remain hidden, inaccessible to any instrument that collects light. Other windows may open. Gravitational wave observatories may detect signals from the first second. Neutrino detectors may achieve the sensitivity needed to observe the cosmic neutrino background. These would extend our reach, pushing the boundary earlier. But for telescopes, the limit is permanent. The cosmic microwave background is the farthest back they can see. No improvement in technology will change this. No larger mirror, no more sensitive detector. No longer observation will penetrate the opacity of the pre-recombination universe. This is the answer to the question. It is precise and physical. It is determined by the universe's history, not by our instruments. It is the limit of how far back telescopes can really see. The cosmic microwave background permeates the universe, and it fills every cubic centimeter of space with approximately 400 photons. These photons have been traveling for 13.8 billion years. Their wavelengths stretched by cosmic expansion, their temperature cooled to 2.7 Kelvin. They are the oldest light we can see. They are the limit of telescopic observation. They are the answer to the question of how far back we can look. And they are beautiful in their implications. They tell us that the universe was once a plasma, once opaque, once unobservable. They tell us that at 380,000 years, the universe became transparent. They tell us that the light from that moment has been traveling ever since, cooling and stretching until it reaches our instruments today. This is the cosmic story written in light. Telescopes read that story, gathering photons that have crossed billions of light years and billions of years. The story begins at recombination, at the cosmic microwave background, at 380,000 years after whatever began it all. Before that, there is no story in light. Before that, light was trapped. Before that, the universe existed, but cannot be observed with electromagnetic radiation. This is the limit of how far back telescopes can really see. It is fundamental, physical, and permanent. It is the boundary of visible history. Within that boundary, the universe offers its history to those who observe. Galaxies forming and evolving, stars igniting and dying, elements being forged and scattered, structures growing under gravity's pull. All of this unfolds after recombination in the transparent universe, accessible to telescopic observation. The cosmic microwave background is the backdrop against which all else occurs. The oldest and most distant signal, the foundation of cosmological knowledge. The question has been answered. Telescopes can see back to 380,000 years after the beginning. They can see the cosmic microwave background, the moment the universe became transparent. They cannot see earlier, no matter how powerful they become. This is the limit. This is the answer. This is how far back telescopes can really see. And in knowing this limit, we understand the shape of our knowledge. We understand what observation can reveal and what must be left to theory. We understand that the universe, vast and ancient as it is, contains an origin that light cannot illuminate. The cosmic microwave background glows in every direction, the oldest thing we can see, the edge of the visible past. Beyond it, the first 380,000 years lie hidden. Beyond that, the very beginning, unknown and perhaps unknowable. This is the structure of the observable universe. This is the boundary of telescopic sight. This is the answer to the question. The photons from recombination continue to arrive, moment by moment, streaming from every direction. They have traveled since before any star existed, since before any galaxy formed, since the universe was a cooling plasma on the verge of transparency. They are the oldest messengers we can receive. They mark the limit of observation. They are the farthest back that telescopes can really see. Within this limit, the exploration continues. The questions that remain are vast. The discoveries that await are profound. The universe offers enough mystery and wonder to occupy inquiry for generations. But the limit itself is fixed. The cosmic microwave background is the boundary. Before it lies opacity. Before opacity lies the beginning. This is how far back telescopes can really see, to the cosmic microwave background, to 380,000 years after the beginning, to the moment the universe became transparent and light was freed to cross the cosmos. That moment is the oldest thing we can observe. It is the limit of the visible past. It is the answer. The universe shows us much. It hides something. What it shows stretches across 13.8 billion years of cosmic history. What it hides is the first 380,000 years, plus whatever came before. Telescopes reveal what is shown. They cannot reveal what is hidden. This is the fundamental structure of electromagnetic observation. Other methods may penetrate the hidden past. Gravitational waves, neutrinos, theoretical inference. These are paths beyond the electromagnetic barrier. But for telescopes, the limit is permanent. The cosmic microwave background is the farthest back they can see. This is the answer to the question of how far back telescopes can really see. It is 380,000 years after the beginning. It is the cosmic microwave background. It is the moment light was released. Beyond that, there is no light to see. The universe existed, but left no visible trace. The first 380,000 years are electromagnetically silent. This is the limit. This is the boundary. This is the edge of the visible past. And within this boundary, the cosmos unfolds before us, ancient and vast, recorded in the light that travels across space and time to reach our instruments. The cosmic microwave background is the oldest part of this record. It is the foundation of observational cosmology. It is the farthest back that telescopes can really see. There is something worth noticing about this boundary that goes beyond its age. The cosmic microwave background is not simply the oldest light. It is a different kind of signal entirely. When we observe a distant galaxy, we are seeing light from a specific object, a collection of stars and gas at a particular location. The galaxy existed before it emitted that light and continues to exist after. We see a moment in its history, but the galaxy itself persists through time. The cosmic microwave background is not like that. It does not come from an object. It comes from everywhere. It was emitted by the entire universe simultaneously, by all the matter that existed at the moment of recombination. There is no galaxy to point at, no star to identify, no single source to track. The cosmic microwave background is the universe itself at 380,000 years, captured in radiation. This distinction matters for understanding what we can and cannot learn. When we observe a galaxy at high redshift, we can in principle observe other galaxies at similar redshifts, piecing together a picture of that epoch from multiple sources. We can compare different regions of the universe at the same cosmic age. We can build statistics, identify patterns, understand the typical and the exceptional. With the cosmic microwave background, there is only one source: the universe at recombination. We can observe it from different directions, measuring temperature and polarization variations across the sky. But we cannot compare it to another universe at the same epoch. We have one sample, one realization of the early universe's conditions. This is not a limitation of our instruments. It is a feature of reality. The cosmic microwave background represents the moment when the universe transitioned from opaque to transparent. Everything before that transition is hidden. Everything after is potentially observable, given sufficient technology. But the transition itself, the surface of last scattering, is unique. What does it mean that this surface is unique? Consider an analogy. Imagine standing in a thick fog. You can see objects near you clearly. As you look farther away, objects become increasingly obscured. At some distance, the fog is so thick that nothing is visible. That distance defines your visual horizon in the fog. Now imagine the fog suddenly lifts. Everything beyond your previous horizon becomes visible. You can see mountains and valleys and cities that were hidden before. The lifting of the fog creates a moment of revelation. The cosmic microwave background is not quite like this. The fog did not lift everywhere at once, revealing a hidden landscape. Instead, the fog itself became the landscape. The plasma that scattered light before recombination became the neutral gas that allowed light to travel. The transition was not a curtain being drawn, but a transformation of the medium itself. Before recombination, photons were constantly interacting with free electrons. Each photon traveled only a short distance before being scattered in a random direction. Information could not propagate through this plasma. Any pattern, any structure, any signal encoded in light would be scrambled by the endless scatterings. At recombination, electrons combined with protons to form neutral hydrogen. Suddenly, photons had nothing to scatter off. They began traveling in straight lines, carrying information about the conditions at the moment of their last scattering. This information has been preserved, unchanged except for the stretching of wavelength due to cosmic expansion for 13.8 billion years. The cosmic microwave background is therefore a snapshot, a frozen image of the universe at one specific moment. It contains enormous information about that moment. The temperature variations reflect density differences. The polarization patterns reflect velocity flows and gravitational wave imprints. The statistical properties of the fluctuations encode the physics of the early universe. But it is a single snapshot. We cannot see what the universe looked like at 300,000 years, or 200,000 years, or 1 second. We can infer these earlier conditions from their effects on the cosmic microwave background, but we cannot observe them directly. This is a subtle point, but an important one. The cosmic microwave background is not a window into the first 380,000 years. It is a wall at 380,000 years, with information about earlier times encoded on its surface. The encoding is indirect. The fluctuations we observe were seeded during inflation and evolved through the plasma epoch. But we do not observe the fluctuations at earlier times, only their final form at the moment of last scattering. So when we ask what information is lost before recombination, the answer is all direct information. We cannot observe light from before recombination because light could not travel before recombination. Any signal that might have been encoded in electromagnetic radiation was erased by the endless scatterings in the plasma. This erasure is fundamental. It is not like data lost in a fire that might, in principle, be recovered from other sources. The information was not recorded elsewhere and then lost. It simply never escaped the plasma. The photons that eventually became the cosmic microwave background were thermalized, brought into equilibrium with the matter around them. Their distribution reflects the temperature and density of the plasma, not any specific events or structures from earlier times. Consider what this means in practice. Suppose some remarkable event occurred in the universe at 100,000 years, a fluctuation or a structure or a process of some kind. Could we ever know about it? Only if it left traces that persisted to 380,000 years and were imprinted on the cosmic microwave background. If the event was local, if it affected only a small region, if its effects were smoothed out by the plasma dynamics before recombination, then no trace would remain. The event would be permanently unobservable. This is a strange kind of loss. We are not talking about events that happened and were forgotten. We are talking about events that happened, but whose effects were erased by the very medium they occurred in. The plasma of the early universe was not just opaque. It was a kind of cosmic eraser, smoothing out information and preventing it from reaching the future. Only the largest scale fluctuations survived. Density variations spanning millions of light years at recombination left imprints on the cosmic microwave background. Smaller scale variations were smoothed by the pressure waves in the plasma, their information lost to the dynamics of the acoustic oscillations that eventually became the observed fluctuation spectrum. This smoothing is another kind of limit. Even at the moment of last scattering, not all information is preserved. The cosmic microwave background contains only the information that survived the plasma epoch, only the patterns that were large enough and strong enough to persist through the dynamics of the early universe. So the 380,000-year limit is actually several limits combined. There is the opacity of the plasma, preventing light from escaping before recombination. There is the thermalization of the photons, erasing specific information about their origins. There is the smoothing of small-scale fluctuations, removing fine structure from the signal. Each of these processes reduces what we can know about the early universe, and each is fundamental. None can be circumvented by better technology. No telescope, however powerful, can see through an opaque medium. No analysis technique can recover information that was thermalized away. No observation can detect fluctuations that were smoothed below the detection threshold. This leads to a question that might seem simple, but has profound implications. If we built a telescope twice as large as any existing one, would we see twice as far back in time? If we built one 100 times larger, would we see 100 times earlier? The intuitive answer might be yes. Larger telescopes collect more light. They can detect fainter objects. Fainter objects are generally more distant. More distant objects show earlier epochs. This reasoning works within the accessible universe. A larger telescope can detect fainter galaxies than a smaller one. It can see galaxies at higher redshifts from earlier times. The relationship is not linear, but the trend holds. Better instruments see earlier epochs. But this reasoning fails at the cosmic microwave background. The issue is not detecting a fainter signal. The cosmic microwave background is not faint. It is the dominant source of photons in the universe, more numerous than all the photons from all the stars and galaxies combined. A larger telescope would not see the cosmic microwave background more clearly. It would simply collect more of the same photons. The limit at 380,000 years is not a limit of detection. It is a limit of existence. There are no photons from before the time to detect. The universe did not emit light that could travel freely before recombination. Building a larger telescope does not create photons that do not exist. This distinction between detection limits and existence limits is crucial. Throughout the history of astronomy, new instruments have revealed previously undetected phenomena. Galileo's telescope showed moons around Jupiter that were invisible to the naked eye. Hubble revealed galaxies that ground-based telescopes could not resolve. Webb detects infrared light that Hubble's instruments could not capture. Each advance revealed something that existed but had not been detected. The moons were there before Galileo observed them. The galaxies were there before Hubble photographed them. The infrared sources were there before Webb turned its mirrors toward them. The cosmic microwave background is different. There is no corresponding advance that will reveal light from before recombination because no such light exists. The obstacle is not detection, but physics. The early universe was opaque, and no telescope can see through opacity. This is what makes the cosmic microwave background a true boundary rather than a current limit. Current limits can be surpassed. Detection thresholds can be lowered. Sensitivity can be increased. But boundaries defined by physics cannot be crossed. They are features of the universe, not limitations of our instruments. So the question of how far back telescopes can see has a permanent answer. At least for electromagnetic telescopes, they can see to the cosmic microwave background, to 380,000 years after the beginning. They will never see earlier with light. This is not pessimism, but precision. Now, within this boundary, there is still much to learn. The cosmic microwave background has not been fully exploited. Its polarization patterns contain information that is still being extracted. The statistical properties of its fluctuations are being measured with increasing precision. Every improvement in measurement yields new constraints on cosmological parameters. Future observations of the cosmic microwave background will tell us more about the universe at 380,000 years and, through inference, about earlier epochs. But they will not push the boundary earlier. The boundary is fixed at the moment of last scattering. This brings us to the question of alternative messengers. We have mentioned gravitational waves and neutrinos as potential carriers of information from earlier times. These are not electromagnetic radiation. They interact with matter differently. Could they reveal what light cannot? Gravitational waves are ripples in space-time itself. They are generated by accelerating masses, particularly by violent events like merging black holes or neutron stars. Unlike photons, gravitational waves are not scattered by matter. They pass through the plasma of the early universe without impediment. If gravitational waves were generated before recombination, they would have traveled freely through the opaque plasma, carrying information from those hidden epochs. Detecting such waves would extend our observational reach backward in time. The challenge is detection. Gravitational waves are extraordinarily weak. Current detectors like LIGO and Virgo can detect waves from relatively nearby sources, within a few billion light years. Detecting a background of primordial gravitational waves generated in the first fraction of a second requires entirely different approaches. One approach involves the cosmic microwave background itself. Primordial gravitational waves would have left subtle imprints on the polarization patterns of the cosmic microwave background. These imprints, called B-mode polarization, have a distinctive pattern that differs from other sources of polarization. Detecting them would be indirect evidence for gravitational waves from the inflationary epoch. The search for primordial B-modes has been ongoing for years. In 2014, the BICEP-2 experiment announced a detection that generated enormous excitement. If confirmed, it would have been the first observational evidence for inflation and for gravitational waves from the early universe. But subsequent analysis showed that dust in our own galaxy could account for the observed signal. The primordial B-mode, if present, was smaller than initially thought. Current experiments continue the search with greater sensitivity and better control of foreground contamination. The Simons Observatory, under construction in Chile, will measure B-mode polarization with unprecedented precision. Other experiments are operating at the South Pole, where the atmosphere is particularly dry and stable. If primordial B-modes are detected, what would they tell us? They would provide evidence that inflation occurred, that the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second. They would constrain the energy scale of inflation, telling us how violent that expansion was. They would be the first direct signal from an epoch before the cosmic microwave background. extending our observational reach by a factor of billions. But even this would not be direct observation of inflation. The gravitational waves themselves would not be detected. Their imprint on the cosmic microwave background would be detected, an indirect signature mediated by the same surface of last scattering that limits electromagnetic observation. Direct detection of primordial gravitational waves would require space-based interferometers, sensitive to much lower frequencies than ground-based detectors. The proposed LISA mission, scheduled for launch in the 2030s, would detect gravitational waves in the millihertz range, corresponding to massive black hole mergers and other phenomena. But even LISA's sensitivity is not designed for the primordial background. More ambitious proposals envision gravitational wave detectors, sensitive to frequencies corresponding to waves generated during inflation. These would require interferometers with arms spanning millions of kilometers, far beyond current technology. Whether such detectors will ever be built remains uncertain. So gravitational waves offer a potential window beyond the cosmic microwave background, but that window remains largely closed. We have indirect evidence that primordial gravitational waves might exist, inferred from inflationary models. We are searching for their imprint on the cosmic microwave background, but direct detection of the waves themselves is far in the future, if it is achievable at all. Neutrinos present a similar picture. These particles interact so weakly with matter that they decoupled from the cosmic plasma far earlier than photons, about 1 second after the beginning. A cosmic neutrino background exists, analogous to the cosmic microwave background but older and colder. Detecting primordial neutrinos would open a window onto the universe at 1 second, 380,000 times earlier than the cosmic microwave background allows. This would be an enormous extension of observational reach. But the challenges are formidable. Primordial neutrinos have extraordinarily low energy, corresponding to temperatures less than 2 Kelvin. Current neutrino detectors are designed for much higher energies, typically from nuclear reactions or astrophysical sources. Detecting neutrinos with energies corresponding to the cosmic background requires entirely new technologies. Various proposals exist. One approach involves capturing neutrinos on tritium nuclei, looking for a tiny shift in the energy spectrum of the emitted electrons. This requires handling large quantities of tritium and achieving energy resolutions at the limits of current technology. The Ptolemy experiment is pursuing this approach, but success is not guaranteed. Even if primordial neutrinos are detected, they would tell us about the universe at 1 second, not earlier. The neutrino background was established when neutrinos decoupled from the plasma, which occurred at about 1 second. Before that, even neutrinos were in thermal equilibrium, their information scrambled by frequent interactions. So neutrinos offer a potential window to 1 second, and gravitational waves might reach back to inflation at tiny fractions of a second. But before that, even these messengers cannot help. The very earliest moments remain hidden from all known forms of observation. This hierarchy of limits reflects the history of the early universe. Different particles and fields decoupled at different times, each decoupling creating a potential observable. Photons decoupled at 380,000 years. Neutrinos decoupled at 1 second. Gravitational waves, if generated during inflation, would have decoupled at tiny fractions of a second. Before each decoupling, The corresponding messenger was in equilibrium with the plasma, unable to carry information forward. After decoupling, the messenger traveled freely, potentially observable today. The decoupling time sets the earliest epoch that each messenger can reveal. This is a beautiful structure. The universe created observational windows at specific moments in its history, releasing different kinds of signals at different times. Each window shows a different epoch. Each has its own challenges of detection. Each extends our reach backward in time by a different amount. But all the windows are finite. All have an earliest accessible moment. None reaches all the way back to the true beginning, whatever that beginning was. This brings us to a deeper question. What is the beginning? When we speak of the universe at 1 second, or at 10 to the minus 36 seconds, or at the Planck time of 10 to the minus 43 seconds, we are using time as a coordinate. We are treating the universe as having existed at all these moments, evolving from some initial state toward the present. But this picture may break down at sufficiently early times. At the Planck time, the density and temperature of the universe were so extreme that quantum effects and gravity become important. Our current theories cannot describe these conditions. General relativity and quantum mechanics, the two great frameworks of modern physics, have not been successfully unified. At the Planck scale, their incompatibility becomes critical. This means we do not really know what the universe was like at the Planck time. We have models and speculations, but no confirmed theory. The notion of time itself may not apply in the usual sense. The question of what happened before the Planck time may not have a meaningful answer. Some cosmological models suggest the universe had no beginning in the conventional sense. The Hartle-Hawking proposal, for instance, describes a universe where time emerges gradually from a timeless quantum state. In this picture, asking what happened before the beginning is like asking what is north of the North Pole. The question assumes a structure that does not exist. Other models propose that our universe emerged from a previous state, perhaps through a bounce from a contracting phase, or as a bubble in a larger multiverse. These models posit a history before what we conventionally call the beginning. But that history may be observationally inaccessible, hidden behind the horizons set by inflation or the Planck scale. We do not know which, if any, of these models is correct. The observations we can make, the cosmic microwave background, and its potential extensions through gravitational waves and neutrinos, constrain the models, but do not uniquely determine them. The ultimate origin remains a matter for theoretical physics, not observational astronomy. This is perhaps the deepest limit of all. Not just that we cannot observe the very early universe, but that we may not even know what questions to ask about it. The concepts we use, time, space, cause, and effect, may not apply. The beginning may not be a moment in time, but something else entirely, something our current understanding cannot fully grasp. So the question of how far back telescopes can see has layers of answers. For electromagnetic telescopes, the limit is 380,000 years. For gravitational wave observations, perhaps fractions of a second. For neutrinos, about 1 second. Beyond that, the early universe becomes progressively more speculative. And at the very beginning, if there is a beginning, our concepts may fail us entirely. This structure of limits is not arbitrary. It reflects the physics of the early universe, the sequence of decoupling events that created observational windows. the opacity that hid earlier epochs. Each limit has a physical explanation. Each arises from the way the universe evolved, and each limit is the same for every observer. An astronomer on a planet in the Andromeda Galaxy, 2.5 million light-years from us, faces the same cosmic microwave background. They see it from a different direction, but it represents the same epoch, the same physics, the same moment of last scattering. An observer in a galaxy at the edge of our observable universe, 46 billion light-years away, has their own cosmic microwave background. It is shifted and delayed relative to ours, but it represents the same transition from opacity to transparency. The limit of 380,000 years applies to them as well. This universality is striking. Every observer, anywhere in the universe, faces the same fundamental limits on how far back they can see. The cosmic microwave background is not a local phenomenon, but a universal one. The opacity of the early plasma affected the entire cosmos, not just our region of it. This means the limits we face are not accidents of our location. They are features of the universe itself. We could not escape them by traveling to a different galaxy or a different part of the cosmos. The boundary at 380,000 years would be there wherever we observe from. There is something reassuring about this universality. It means the limits are not arbitrary, not imposed by the particularities of our situation. They are deep truths about the cosmos, applicable everywhere. Understanding them tells us something fundamental about the nature of observation and the structure of the universe. It also means that any other observers, any other civilizations that might exist in the cosmos, face the same limits we do. If intelligent beings in a distant galaxy are studying cosmology, they are confronting the same cosmic microwave background, the same boundary at 380,000 years, the same challenges of detecting gravitational waves and neutrinos. This shared predicament is a kind of cosmic democracy. No observer is privileged. No location offers a better view of the early universe. The limits are universal, and within those limits, every observer sees the same fundamental structures and patterns. Now, within this framework of limits, there is something important to notice. The limits do not make the universe smaller or less interesting. They define the territory of observation, but that territory is vast. Consider what we can observe. Billions of galaxies spanning billions of years of cosmic history. The cosmic microwave background with its wealth of information about the early universe. The large-scale structure of matter, tracing the growth of cosmic structure from tiny seeds. The expansion of space accelerating under the influence of dark energy. All of this lies within the observable universe, within the boundaries set by the speed of light and the opacity of the early plasma. The territory is not infinite, but it is enormous. It contains more than we can ever fully explore. And within this territory, every observation is meaningful. Every galaxy detected is a data point in the history of cosmic evolution. Every fluctuation in the cosmic microwave background is a clue to the physics of the early universe. Every measurement of the expansion rate constrains the properties of dark energy. The limits do not diminish the value of what lies within them. If anything, they enhance it. Knowing that there is a boundary gives shape to the exploration. It distinguishes what can be known from what cannot. It allows us to focus our efforts on the questions that can be answered. This is perhaps the most important realization about cosmological limits. They are not obstacles to be lamented, but structures to be understood. They arise from physics, They apply universally. They define the scope of observation. And within that scope, there is more than enough to discover. The question of how far back telescopes can see is answered by these limits. The answer is not a single number, but a hierarchy. 380,000 years for light, potentially 1 second for neutrinos, potentially fractions of a second for gravitational waves. Before that, the early universe becomes progressively more hidden, and the very beginning may lie beyond all observational reach. This answer is precise in some respects and uncertain in others. The 380,000-year limit for electromagnetic radiation is firm. The potential reach of gravitational waves and neutrinos is less certain, depending on detection capabilities that have not yet been achieved. The nature of the very early universe remains a matter for theoretical speculation. But the structure of the answer is clear. There are limits. They arise from physics. They cannot be circumvented by technology. They define what can be known through observation and what must be left to theory. And this structure is not disappointing. It is clarifying. It tells us what questions to ask and what methods to use. It distinguishes empirical cosmology from theoretical speculation. It gives shape to the scientific enterprise. The cosmic microwave background is the foundation of this structure. It is the oldest and most fundamental signal we can observe with light. It marks the boundary between the visible and the hidden past. It is the answer to the question of how far back telescopes can really see. Beyond that boundary, other messengers might extend our reach. Gravitational waves and neutrinos offer potential windows to earlier epochs. Theoretical physics offers frameworks for understanding what we cannot observe. But the boundary itself remains. There is a kind of peace in accepting this boundary, not the peace of giving up, but the peace of understanding. The universe has a structure. That structure includes limits on observation. Those limits are not failures, but features. They define the territory of knowledge. Within that territory, the exploration continues. Every observation adds to our understanding. Every new instrument reveals previously hidden details. Every theoretical advance connects observations to deeper principles. The cosmic microwave background sits at the edge of this territory, the farthest visible surface, the oldest detectable light. It is there because the universe evolved in a particular way, because plasma preceded neutral gas, because opacity preceded transparency. And it will always be there, the permanent limit of electromagnetic observation. Future telescopes will study it with greater precision, extracting more information from its patterns. But they will not see beyond it. The boundary is fixed. This is the answer to the question of how far back telescopes can really see. To the cosmic microwave background, to 380,000 years after the beginning, to the moment the universe became transparent. The universe before that moment existed. Events occurred. Conditions were established. But no light survives from those times. The plasma absorbed and re-emitted every photon, erasing the information they might have carried. This erasure is complete. It is not a matter of faint signals awaiting better instruments. It is a matter of signals that never existed, photons that never escaped. The early universe left no electromagnetic record because it could not leave such a record. So the telescopes that observe the cosmic microwave background are not seeing through a barrier. They are seeing the barrier itself. The surface of last scattering is not a window into earlier times, but a wall against them. The wall is made of light. the first light that could travel freely, and behind it lies darkness. Not the darkness of empty space, but the darkness of opacity, of plasma, of scattered and rescattered photons. The early universe was full of light, but that light could not escape. It was confined, thermalized, its information content erased by the very processes that created it. Only at recombination did the light break free. Only then did photons begin the journeys that would eventually bring them to our instruments. Only then did the universe become visible. This moment of visibility is what the cosmic microwave background represents. It is the dawn of observability, the first instant when the universe could be seen from afar. Everything before was hidden, and everything before will remain hidden to electromagnetic observation. The boundary is not just at 380,000 years. It is at every earlier moment. We cannot see 300,000 years. We cannot see 100,000 years. We cannot see 1 year, or 1 day, or 1 second with light. The opacity extended all the way back, blocking all electromagnetic observation of all earlier epochs. This is the complete answer to the question. Telescopes using light can see to 380,000 years and no earlier. The limit is absolute for electromagnetic radiation. Other messengers might extend observation to earlier times, but they have their own limits. And the very earliest moments may be beyond all observation. The universe has an observational horizon built into it. Not a horizon in space, but a horizon in time. Beyond that horizon lies the past we cannot see, the epochs that left no observable record. This horizon is not a failure of human ingenuity. It is a feature of cosmic history. The universe evolved through phases, from hot and opaque to cool and transparent. The transition between phases created the cosmic microwave background, the oldest light we can see. Accepting this horizon is part of understanding the cosmos. It means recognizing that some questions cannot be answered through observation alone. It means distinguishing between what we can know and what we must speculate about. It means understanding the limits of empirical science. These limits are real. They are not merely current, but permanent. No future technology will see through the opacity of the early plasma. No instrument will detect light that does not exist. But within these limits, the universe offers itself to observation. The cosmic microwave background is rich with information. The galaxies and quasars of the accessible universe reveal billions of years of evolution. The structure of matter and energy on cosmic scales constrains the physics of the early universe. The territory of observation is vast. It stretches from the present moment back to 380,000 years after the beginning. It encompasses the formation and evolution of galaxies, the enrichment of the cosmos with heavy elements, the emergence of complexity from primordial simplicity. All of this lies within the observable universe, within the limits set by physics. The limits do not diminish this territory. They define it. And within its boundaries, there is more than we can ever fully explore. The cosmic microwave background marks the edge of this territory. It is the farthest we can see with light. It is the oldest signal we can detect electromagnetically. It is the answer to how far back telescopes can really see. Beyond that edge, the universe existed, but cannot be observed with light. The first 380,000 years are hidden behind the fog of the early plasma. What happened in those years? What conditions prevailed? What fluctuations occurred can only be inferred from their effects on later observables. This inference is powerful. The patterns in the cosmic microwave background encode information about earlier times. The abundances of light elements reflect conditions in the first few minutes. The overall expansion history constrains the physics of the first second. But inference is not the same as observation. We can construct models consistent with the data. We cannot see the earlier epochs directly. The limit remains. And the limit is the answer. Telescopes can see back to 380,000 years. They can see the cosmic microwave background. They cannot see earlier with light. This is the fundamental structure of electromagnetic observation. It emerged from the physics of the early universe. It applies to all observers everywhere. It defines the boundary between visible and hidden history. The cosmos is deep, deeper than we can see, deeper than any telescope will ever reveal. The 380,000 years before recombination, plus whatever came before that, lie beyond electromagnetic observation. This depth is not emptiness. It is history, evolution, physics, playing out in conditions we cannot observe. The universe did not begin at 380,000 years. It began earlier, perhaps infinitely earlier, or perhaps at a moment where the concept of before does not apply. Whatever the case, the observable universe has an edge in time. That edge is the cosmic microwave background, 380,000 years after the beginning. Beyond it lies the past we cannot see. Telescopes have brought us to this edge. They have shown us the oldest light in the universe. They have revealed the patterns that encode information about even earlier times. They have given us a picture of the cosmos stretching back 13.8 billion years, but they stop at 380,000 years. The cosmic microwave background is their limit. Beyond it, light cannot guide us. This is what it means to ask how far back telescopes can really see. The answer is to the cosmic microwave background, to the moment the universe became transparent, to 380,000 years after everything began. The early universe lies beyond that moment, hidden in opacity. Other messengers might reveal fragments of it. Theoretical physics might describe it. But telescopes, instruments of light, cannot penetrate it. The universe has a boundary that no telescope can cross. That boundary is the cosmic microwave background. It is the oldest light. It is the limit of observation. It is where the visible past ends and the hidden past begins. There is another kind of boundary worth considering, one that operates not in the past, but in the future. The cosmic microwave background limits how far back we can see. But there is also a limit on how far we can ever see. A horizon that is not fixed, but moving, shaped by the expansion of space itself. This horizon has a different character than the surface of last scattering. The cosmic microwave background is a wall in time, set by the physics of recombination 380,000 years after the beginning. The other horizon is a wall in space, set by the rate at which the universe expands. And unlike the cosmic microwave background, this spatial horizon is changing. It is growing closer. To understand this, consider how light travels through an expanding universe. When a photon leaves a distant galaxy, it begins a journey toward us. But during that journey, space itself is stretching. The distance between the galaxy and us is increasing even as the photon crosses it. Whether the photon reaches us depends on the race between its speed and the expansion of space. For most of cosmic history, light has won this race. Photons from distant galaxies eventually reach us despite the expansion. The journey takes longer than it would in a static universe, but it still completes. This is why we can observe galaxies billions of light years away. Their light has been traveling for billions of years, crossing expanding space, and eventually arriving at our instruments. But the universe's expansion is accelerating. Dark energy, the mysterious component that makes up about 68% of the universe's energy content, is causing space to stretch faster and faster. This acceleration changes the outcome of the race. Consider a galaxy at a certain distance today. Its light is traveling toward us, but the space between us is expanding, and that expansion is speeding up. At some point, the expansion rate exceeds the speed at which light can cross the intervening distance. The photon, still traveling at the speed of light, falls behind. It will never reach us. This defines an event horizon. Objects beyond this horizon are not just currently invisible, they are forever invisible. Their light, emitted today, will never arrive. The space between us will expand faster than their photons can traverse it. This horizon is not at a fixed distance. It depends on the expansion history of the universe, which depends on the properties of dark energy. Current measurements suggest the event horizon is roughly 16 billion light-years away. Galaxies currently within this radius might send light that will eventually reach future observers. Galaxies beyond it have already crossed into permanent invisibility. But this is not the whole story. The event horizon describes light emitted now. What about light emitted in the past? Galaxies that are currently beyond the event horizon may have sent light long ago that will still reach us. The crucial question is when the light was emitted relative to when the galaxy crossed the horizon. This creates a strange situation. We can observe galaxies that are currently beyond the event horizon because their light was emitted before they crossed it. We see them as they were in the distant past, when they were closer and their light could still reach us. But we will never see them as they are now, or as they will be in the future. Over time, more and more galaxies will cross the event horizon. Their light, still en route to us, will eventually arrive. But once it does, no new light from those galaxies will follow. They will fade from view, not because they have changed, but because space has carried them beyond the reach of observation. This fading is not immediate. It happens gradually, as the expansion accelerates and more distant galaxies cross the threshold. Billions of years from now, the observable universe will contain fewer galaxies than it does today. Not because galaxies have been destroyed, but because they have become invisible. The local group, the collection of galaxies gravitationally bound to the Milky Way, will remain visible. Gravity holds these galaxies together, counteracting the expansion of space on local scales. The Andromeda Galaxy, for instance, is actually approaching us, drawn by mutual gravitational attraction. It will merge with the Milky Way in about 4 billion years. But galaxies beyond the local group are not bound to us. The expansion of space carries them away, slowly at first, then faster, as acceleration takes hold. Eventually, only the merged remnant of the Milky Way and Andromeda will remain visible, a single supergalaxy, isolated in an apparently empty cosmos. This future is billions of years away, far beyond any timescale relevant to human civilization. But it illustrates something important about observational limits. The universe is not static. The boundaries of observation are not fixed. What is visible today may become invisible tomorrow on cosmic timescales. The cosmic microwave background limits how far back we can see. The event horizon limits how far out we will be able to see in the future. These two limits operate in different directions, one in time and one in space, but both constrain what observation can reveal, and there is a connection between them. The cosmic microwave background represents light from matter that is now about 46 billion light-years away. This matter is beyond the current event horizon. We will never receive new light from it. The cosmic microwave background is the last signal we will ever get from those regions. This is worth pausing on. The cosmic microwave background is not just the oldest light we can see. It is, in many cases, the last light we will ever see from the matter that emitted it. The regions that produce the cosmic microwave background have been carried so far away by expansion that they are now beyond our event horizon. They are doubly hidden, once by the opacity of the pre-recombination universe, and again by the expansion that has moved them beyond future visibility. So the cosmic microwave background occupies a special place in observational cosmology. It is both the first light that could reach us from the early universe and the last light that will reach us from those distant regions. It is a boundary in both directions. This dual nature makes the cosmic microwave background even more significant than its age alone would suggest. It is not merely old, it is unique. Nothing from before it can be observed with light, and nothing from after it, from those same regions, will ever be observed either. The matter that emitted the cosmic microwave background has continued to evolve. It has formed stars and galaxies, produced heavy elements, perhaps even developed life. But we will never know. The light from those subsequent developments will never reach us. The expansion of space has sealed those regions away from our observation permanently. This is a different kind of limit than the opacity of the early universe. The opacity is a historical fact, a condition that existed in the past and prevented light from escaping. The event horizon is an ongoing process, a consequence of accelerating expansion that continues to hide more and more of the universe. Both limits are fundamental. Neither can be overcome by better technology. The opacity cannot be penetrated by any electromagnetic instrument. The event horizon cannot be outrun by any observation. They are features of the universe, not limitations of our methods. But they operate differently. The opacity is fixed. The conditions that created it existed 380,000 years ago and have not changed since. The event horizon is dynamic. It is created by the ongoing expansion of space, which itself is accelerating. The horizon is moving inward, encompassing more and more of the universe with each passing moment. On cosmic timescales, this inward movement is significant. Billions of years from now, the event horizon will be closer than it is today. Galaxies currently visible will have crossed it. The observable universe will have shrunk, not because its physical extent has changed, but because more of it will have become permanently inaccessible. This shrinking is irreversible. Once a galaxy crosses the event horizon, it cannot cross back. The expansion of space is carrying it away faster than any signal from it could return. It is gone from observation forever. There is something poignant about this, if we allow ourselves to reflect on it. The universe is vast, filled with billions of galaxies, each containing billions of stars. Many of these galaxies are already beyond the event horizon, their current states forever unknown to us. Many more will cross the horizon in the future, adding to the catalog of things we will never see. The observable universe is not expanding to include more. it is contracting to include less. The contraction is slow by human standards, imperceptible over any timescale we can experience directly. But it is real, and it is ongoing. This is not cause for despair. The observable universe is still vast, still filled with more than we can ever explore. The contraction operates on timescales of billions of years, far beyond any concern for current or near-future observers. But it does change how we think about observation. The question of how far back telescopes can see has a companion question. How far will telescopes ever be able to see? The answer to the first question is the cosmic microwave background, 380,000 years after the beginning. The answer to the second question is more complex, depending on when the observation is made and how the expansion evolves. For observers today, the particle horizon defines the limit of the observable universe. This is the maximum distance from which light has had time to reach us since the beginning. It is currently about 46 billion light years, corresponding to the co-moving distance to the cosmic microwave background. The particle horizon grows over time. As the universe ages, light from more distant regions has time to arrive. In principle, the particle horizon should expand forever, encompassing more and more of the universe. But the event horizon complicates this picture. Even as the particle horizon expands, the event horizon contracts. New light can arrive from regions that were previously too far away, but at the same time, light from other regions that we could once see will stop arriving. The interplay between these two horizons determines what we can observe at any given moment. Currently, the particle horizon is larger than the event horizon. We can see light from regions that are now beyond the event horizon, because that light was emitted long ago, before those regions crossed the threshold. In the far future, this relationship will change. The observable universe will be determined increasingly by the event horizon rather than the particle horizon. Observers, billions of years from now, will see a different cosmos, one in which most of the galaxies visible today have faded from view. This evolution of the observable universe is a direct consequence of accelerating expansion. If expansion were decelerating, as it was in the past, the situation would be different. The event horizon would be further away or might not exist at all. More of the universe would remain permanently accessible. But dark energy changed this. The transition from decelerating to accelerating expansion occurred about 5 billion years ago. Since then, the event horizon has been moving inward, slowly claiming more of the universe for permanent invisibility. The cause of this acceleration remains one of the great mysteries of cosmology. Dark energy is a name for our ignorance. It describes the observed acceleration, but does not explain it. Various theoretical proposals exist, from a cosmological constant to dynamic fields to modifications of general relativity. None has been definitively confirmed. What is confirmed is the effect. The universe is expanding faster and faster. This acceleration creates an event horizon. That horizon limits what future observers can ever see. These are observational facts, even if the underlying physics is not yet understood. So the question of how far telescopes can see has both a past answer and a future answer. The past answer is the cosmic microwave background, the surface beyond which the early universe's opacity blocks all light. The future answer is the event horizon, the surface beyond which accelerating expansion prevents light from ever arriving. These two boundaries define the observable universe in time and space. The cosmic microwave background sets the limit of looking back. The event horizon sets the limit of looking out. Together, they bound the region of the cosmos that any electromagnetic observation can ever access. Within these bounds, there is still enormous territory. Billions of galaxies remain visible. Billions of years of cosmic history can be traced. The structure and evolution of the universe on the largest scales can be studied. The observable cosmos, though bounded, is far from exhausted. But the bounds are real. They cannot be expanded by better technology. They are features of the universe, arising from physics rather than engineering. Recognizing them is part of understanding what observation means in cosmology. There is another subtlety worth noting. The distances involved in cosmology are not straightforward. When we say a galaxy is 46 billion light-years away, we are using co-moving distance, which accounts for the expansion of space. The light travel distance, the actual path length that photons traversed, is different. It is closer to 13.8 billion light-years, the age of the universe times the speed of light. These different distance measures can be confusing, but they reflect real physical facts. The universe has expanded during the time light was traveling. The matter that emitted the cosmic microwave background was much closer when it emitted that light than it is now. The expansion of space has carried it outward, even as its light was traveling toward us. This is not intuitive. In everyday experience, distances are fixed. An object a mile away is a mile away regardless of when we measure it. But in cosmology, distances change with time. Space itself stretches, carrying objects along with it. This stretching affects not just distances, but also the light traveling through them. The redshift of distant objects is caused by this stretching. Photons emitted at certain wavelengths arrive at longer wavelengths because space has stretched during their journey. The longer the journey, the more stretching, and the greater the redshift. The cosmic microwave background has a redshift of about 1/100. This means the wavelengths of its photons have been stretched by a factor of 1,100 since they were emitted. Light that was visible at recombination, glowing at temperatures of thousands of kelvins, is now microwave radiation, cold and diffuse. This stretching is not merely a technical detail. It determines what we can observe and how we interpret it. Telescopes operating at different wavelengths see different populations of objects, not because those objects emit at different wavelengths, but because redshift has shifted their light into different parts of the spectrum. The James Webb Space Telescope operates in the infrared precisely because the most distant galaxies have been redshifted into infrared wavelengths. Their light, originally ultraviolet or visible, has been stretched by billions of years of cosmic expansion. To see these ancient objects, we must observe at wavelengths where their shifted light now resides. This is another way that the expansion of the universe shapes observation. It does not merely determine distances, it determines what kinds of light we receive from distant sources. The universe acts as a filter, stretching wavelengths as light travels, transforming the signals we receive. At extreme distances, this stretching becomes problematic. Light from the most distant objects is stretched so much that it fades below detection thresholds. Photons spread across longer wavelengths carry less energy per unit wavelength. At some point, the signal becomes too dilute to detect. This is another kind of limit, a practical one rather than a fundamental one. The cosmic microwave background and the event horizon are fundamental limits set by physics. Detection thresholds are practical limits set by technology. In principle, practical limits can be overcome by better instruments. In practice, the improvements needed may be beyond foreseeable technology. The distinction matters conceptually. When we ask how far back telescopes can see, we are asking about fundamental limits. The answer, for electromagnetic telescopes, is the cosmic microwave background. This is not a detection limit that might be surpassed. It is a physical barrier that cannot be crossed. Within that barrier, there are practical limits as well. Current telescopes cannot detect the very faintest signals from the most distant sources. Future telescopes might push these practical limits further, but no telescope, however advanced, will see beyond the cosmic microwave background with light. This hierarchy of limits structures our understanding of cosmic observation. Fundamental limits are fixed, arising from physics. Practical limits are movable, arising from technology. Both constrain what we can observe, but in different ways. The cosmic microwave background represents a fundamental limit that has been reached. We have observed it. We have mapped it in extraordinary detail. We have extracted an enormous amount of information from it, but we cannot see beyond it. The event horizon represents a fundamental limit that is approaching. Galaxies are crossing it, becoming permanently invisible. The observable universe is shrinking on cosmic timescales. This limit will increasingly constrain what future observers can see. Between these limits, the accessible universe remains vast. Current telescopes are far from detecting everything within this region. Practical limits prevent observation of the faintest and most distant accessible sources. Future instruments will push these practical limits, revealing more of the accessible cosmos. But the fundamental limits will remain. The cosmic microwave background will always mark the edge of the visible past. The event horizon will continue to contract, claiming more of the universe for permanent obscurity. These are features of the cosmos, not problems to be solved. Understanding this helps clarify what telescopes actually do. They collect light from the accessible universe. They push practical limits of detection. They reveal more and more of what lies within the fundamental boundaries, but they do not move the boundaries themselves. A telescope with a mirror, a kilometer across, would detect fainter objects than current instruments. It would push practical limits significantly, but it would not see before the cosmic microwave background or beyond the event horizon. Those limits are set by physics, not by mirror size. This is why the question of how far back telescopes can see has a definite answer. The answer is not limited by current technology, but by the structure of the universe. Better technology can reveal more within the accessible region, but cannot expand that region. The accessible region is bounded by history on one side and expansion on the other. The cosmic microwave background marks where history ends for light, where the early universe's opacity blocked all electromagnetic signals. The event horizon marks where expansion wins, where space stretches faster than light can cross. These two boundaries define the observable cosmos. Everything within them is potentially observable, given sufficient technology. Everything outside them is permanently hidden, regardless of technology. This structure is not arbitrary. It arises from physics. The cosmic microwave background exists because the early universe was a plasma that scattered light. The event horizon exists because dark energy causes accelerating expansion. Both are consequences of how the universe evolved and continues to evolve. Recognizing this structure is part of understanding what cosmology can achieve. It can explore the observable cosmos in ever greater detail. It can constrain the physics of the early universe through observations of the cosmic microwave background. It can trace the evolution of galaxies and large-scale structure through observations of the accessible epoch. But it cannot observe the unobservable. It cannot see before the cosmic microwave background with light. It cannot see beyond the event horizon, now or ever. These limits define the scope of the enterprise. There is something clarifying about limits. They distinguish what can be done from what cannot. They focus effort on the achievable. They prevent wasted pursuit of the impossible. In cosmology, the limits are particularly clear. The cosmic microwave background is not a fuzzy boundary, but a sharp one, defined by the physics of recombination. The event horizon is mathematical, defined by the equations of cosmic expansion. These limits can be calculated, predicted, and understood. Within these limits, there is more than enough to explore. The observable universe contains on the order of 2 trillion galaxies, each with hundreds of billions of stars. The cosmic microwave background encodes information about the physics of the early universe that we are still extracting. The large-scale structure of matter traces the growth of cosmic structure over billions of years. All of this lies within the accessible cosmos. All of it can be studied with better instruments and more sophisticated analysis. The territory is bounded, but far from exhausted. The question of how far back telescopes can see is answered by the cosmic microwave background. The question of how far out telescopes will ever be able to see is answered by the event horizon. Together, these answers define the observable universe, the region accessible to electromagnetic observation. This region is vast. It stretches from the present moment back to 380,000 years after the beginning. It encompasses billions of light-years of space and billions of years of time. It contains the entire history of galaxies and stars that we can ever know through light. But it is bounded. Beyond the cosmic microwave background lies the hidden past. Beyond the event horizon lies the hidden present and future. These hidden regions exist, contain matter and energy, and perhaps observers of their own, but are forever beyond the reach of our telescopes. This is the structure of observational cosmology. It is determined by physics. It applies to all observers everywhere. It defines what can be known through electromagnetic observation. The cosmic microwave background is central to this structure. It is the oldest observable signal. It is the boundary of the visible past. It is the source of much of our cosmological knowledge, and it is the answer to how far back telescopes can really see. Not the current state of the art, but the fundamental limit. Not what we have achieved, but what is achievable. The cosmic microwave background, 380,000 years after the beginning, marks the edge. Beyond that edge lies the early universe, opaque and hidden. Before recombination, light could not travel. No electromagnetic signal escaped. The information from those epochs is erased, thermalized, lost. Other messengers might reveal fragments of that hidden past. Gravitational waves might carry information from inflation. Neutrinos might carry information from the first second, but these are potentials, not achievements. The electromagnetic boundary, at 380,000 years, is the only one we have fully reached and mapped. That boundary is the cosmic microwave background. It is there because the universe evolved from plasma to atoms, from opacity to transparency. It is the first light that could travel freely, and it carries information about the moment of transition. This moment is what telescopes can reach when they look as far back as possible. Not the beginning, but the dawn of visibility. Not the origin, but the first instant of observable history. The cosmic microwave background marks where observation begins. Everything before is hidden. Everything after is potentially observable. The boundary between them is set by physics, not technology. It cannot be moved by better instruments or longer observations. This is the definitive answer to how far back telescopes can really see. The cosmic microwave background. 380,000 years after the beginning, the moment the universe became transparent. Beyond that, there is no light to see. The universe existed, but left no electromagnetic record. The first 380,000 years are lost to observation, hidden behind the fog of primordial plasma. This is the limit. It is fundamental and permanent. It defines what electromagnetic observation can achieve. Within this limit, much remains to be discovered. The observable universe is vast and largely unexplored. Better instruments will reveal more of it. Better analysis will extract more information from existing observations. The territory is bounded, but far from mapped. But the limit itself is fixed. The cosmic microwave background marks the edge. Beyond it lies what no telescope will ever show us: the hidden past of the universe, inaccessible to light. There is a geometry to all of this that becomes clearer when considered carefully. The observable universe is often described as a sphere centered on our location, with a radius of about 46 billion light-years. This description is accurate, but can be misleading. The sphere is not a physical boundary. It is a horizon, defined by the finite speed of light and the finite age of the universe. An observer at the edge of our observable universe would have their own observable sphere, overlapping substantially with ours, but extending in different directions. Every observer has their own horizon. There is no privileged location, no center to the universe. Each point in space is surrounded by its own observable region, determined by how far light has traveled since the beginning. This means the universe beyond our observable sphere exists, filled with galaxies and stars and matter, but is invisible to us. Observers in those distant regions can see things we cannot, and we can see things they cannot. No observer has access to the whole. The cosmic microwave background defines the boundary of each observer's sphere. An observer, 20 billion light-years from us, sees their own cosmic microwave background, coming from a slightly different region of matter at the same redshift and temperature. The physics is universal, only the location differs. This universality is important. The limits we face are not peculiar to our position. They are structural features of cosmology, applying everywhere. Any observer, anywhere in the universe, faces the same 380,000-year barrier to electromagnetic observation. This shared limit connects us to hypothetical observers we will never contact. Whoever else is out there, studying the universe with their own instruments, confronts the same boundary. The cosmic microwave background is not our horizon, but the horizon, a universal feature of electromagnetic observation. And beyond that horizon, the same hidden past exists. The first 380,000 years are hidden from all observers, everywhere. No location offers a privileged view into the opaque epoch. The plasma scattered light everywhere, preventing any signal from escaping anywhere. This is what it means for a limit to be fundamental. It is not specific to us. It arises from physics that applies universally. It cannot be escaped by traveling to a different location because every location faces the same constraint. The event horizon shares this universality with a caveat. Every observer has their own event horizon, defined by the expansion of space relative to their location. The horizons differ in detail, but exist for everyone. Accelerating expansion creates boundaries for all observers, not just us. These universal limits give cosmology its particular character. It is a science constrained by horizons, both in time and space. The observable universe is vast but bounded. The accessible history is long but finite. The regions beyond the boundaries exist but cannot be studied directly. Within these constraints, cosmology has achieved remarkable success. The standard model, Lambda CDM, accounts for observations from the cosmic microwave background to the present distribution of galaxies. The age, composition, and geometry of the universe are known with precision. The evolution of cosmic structure is understood in broad outline. All of this knowledge comes from observations within the accessible region. The cosmic microwave background provides the earliest data point. Distant galaxies and quasars provide intermediate points. The local universe provides the most recent data. Together, they trace cosmic history from 380,000 years to now. This history is rich and complex. Galaxies formed and evolved. Stars ignited and died. Elements were forged and scattered. Structure grew under gravity's influence. Life emerged, at least on one planet, and developed the capacity to study the cosmos. All of this happened within the accessible epoch, the time after recombination when light could travel and observation was possible. The history is knowable because the signals survived. Before that, history continues but becomes invisible. The first 380,000 years saw nucleosynthesis, the formation of light elements. They saw the matter-antimatter asymmetry take hold. They saw whatever processes generated the density fluctuations that became galaxies. These events occurred. They shaped the universe we observe, but they left no direct electromagnetic trace. We infer them from their effects on later observables, from the abundances of elements and the patterns in the cosmic microwave background. Inference is powerful, but not the same as direct observation. The cosmic microwave background is where direct observation begins. It is the starting point of the electromagnetic record. Everything before it is reconstruction, inference, theory applied to later data. This gives the cosmic microwave background its foundational role. It is not merely old. It is the oldest thing we can observe directly. It is not merely distant. It is the most distant surface we can see. It anchors the entire observational enterprise of cosmology. And it is the answer to how far back telescopes can see. Not what they have seen, or what they might see with improvements, but what they can ever see in principle. The cosmic microwave background is the limit, the boundary, the edge of electromagnetic observation. Within that boundary, better telescopes will see more. They will detect fainter galaxies, resolve finer structures, measure more precise spectra. The accessible universe will be mapped in increasing detail. But the boundary will not move. This permanence is not a flaw in cosmology. It is a feature, a structural element that gives the science its character. Cosmology explores a bounded region constrained by physics. Within those constraints, it has been remarkably successful. The constraints themselves tell us something about the universe, about how it evolved, and how observation works within it. The cosmic microwave background tells us the universe was once opaque. The event horizon tells us space is expanding and accelerating. Both are limits that also convey information. Understanding them is part of understanding the cosmos. So the question of how far back telescopes can see is answered, and the answer is significant beyond the specific number. It reveals the structure of observation, the boundaries of the accessible, the relationship between physics and what can be known. Telescopes see to the cosmic microwave background 380,000 years after the beginning. They will always see to this limit and never beyond it. The limit is fundamental, universal, and permanent. Within this limit, the cosmos unfolds. Billions of years of history, billions of galaxies, the emergence of structure and complexity. The observable universe is vast and largely unexplored, a territory bounded but far from exhausted. Beyond the limit, the early universe remains hidden. Other methods might reveal fragments, glimpses through alternative messengers. But for telescopes, instruments of light, the cosmic microwave background is the end of the visible past. This is the answer. It is clear, physical, and definitive. It tells us what observation can achieve and where it must stop. It defines the boundary of electromagnetic cosmology. The universe continues beyond that boundary. Matter and energy exist in regions we cannot see. History occurred in epochs we cannot observe. The cosmos is larger and older than the observable portion suggests. But we are confined to what light can show us, and light can show us back to 380,000 years, to the cosmic microwave background, to the moment of last scattering. There, observation begins. Before there, observation is impossible. This is the structure of the visible universe, a bounded region in time and space, a history accessible through light, an edge defined by the physics of the early cosmos. The cosmic microwave background is that edge. It is the oldest signal. It is the limit of observation. It is the answer to how far back we can see. And in being the limit, it reveals what limits mean in cosmology. Not failures, but boundaries. Not problems, but features. Not obstacles, but definitions of what the observable universe is. The observable universe is what light can reach. Light can reach from 380,000 years onward, from recombination to now. Before recombination, there is no light to reach us. After the event horizon, light will not reach future observers. These boundaries define the scope of electromagnetic astronomy. They tell us what questions can be answered through observation and what must be left to theory. They give shape to the scientific enterprise. Within that shape, much remains. The accessible cosmos is enormous, filled with phenomena to study and patterns to understand. Telescopes will continue to reveal its contents, pushing practical limits ever further. But the fundamental limits are fixed. The cosmic microwave background marks the past boundary. The event horizon marks the spatial boundary. Together, they define the observable universe. This is the deepest answer to the question of how far back telescopes can see. Not just a number, but a structure. Not just a limit, but a definition. The observable universe has boundaries, and those boundaries are where observation ends. The cosmic microwave background is one such boundary. It is the oldest thing we can see. It is where the visible past stops. It is the answer. Beyond it, the universe continues but cannot be observed with light. The hidden past exists, filled with events and process that shaped everything that followed. But no electromagnetic signal survives from those epochs. The plasma erased them. This is the final character of the limit. Not that we have not yet seen beyond it, but that we cannot see beyond it. Not that better technology might help, but that no technology can penetrate it. The limit is physical, fundamental, and permanent. Telescopes see to the cosmic microwave background. They will always see to this limit. They will never see beyond it with light. This is the structure of electromagnetic observation, and it cannot be changed. Within this structure, cosmology flourishes. The accessible universe provides more than enough to study. The cosmic microwave background itself contains vast amounts of information. Galaxies and clusters and the large-scale structure of matter offer endless opportunities for investigation. But the structure has edges. The cosmic microwave background is one edge. The event horizon is another. These edges are not obstacles to be overcome, but features to be understood. They tell us something about the universe, about how it evolved, and what observation means within it. The question of how far back telescopes can see leads to these edges. It finds, at the limit of the past, the cosmic microwave background, 380,000 years after the beginning. It finds, at the limit of the future, the event horizon, slowly claiming more of the universe for permanent invisibility. Between these limits, the observable cosmos exists. It is vast and ancient, filled with wonders and mysteries. Telescopes explore it, pushing practical boundaries, revealing more of what lies within the fundamental ones. And the fundamental boundaries remain, fixed by physics, universal for all observers, defining the scope of what can ever be known through electromagnetic observation. The cosmic microwave background is the past boundary, the moment the universe became transparent, the first light that could travel, the oldest signal we can ever receive with telescopes. This is where observation begins. This is how far back telescopes can really see. This is the edge of the visible past. The universe before that edge is hidden. The events of the first 380,000 years left no electromagnetic trace. They shaped everything that followed but cannot be directly observed. The universe beyond the event horizon is becoming hidden. Galaxies are crossing it, their light ceasing to reach us. The observable cosmos is shrinking slowly on timescales beyond human concern. Between these edges, the accessible region remains. Vast, complex, only partially explored. The territory of observational cosmology, the region where telescopes reveal the history and structure of the cosmos. The cosmic microwave background anchors this territory. It is the oldest observable signal. It marks the beginning of the visible past. It is the answer to how far back we can see. And in being the answer, it also reveals what it means to answer such questions. Not just to provide a number, but to explain a structure. Not just to state a limit, but to understand why it exists. The cosmic microwave background exists because the early universe was a plasma. It marks 380,000 years because that is when recombination occurred. It limits observation because no light could escape before it. These reasons are physical. They arise from the evolution of the universe, from the cooling of plasma to the formation of atoms. They are not arbitrary, but follow from fundamental physics. Understanding this gives depth to the answer. The cosmic microwave background is not just a boundary, but a consequence. It tells us about the early universe, even as it prevents us from seeing further into that early time. This is the character of cosmological limits. They are not mere barriers, but sources of information. The cosmic microwave background teaches us about recombination. The event horizon teaches us about dark energy. The limits themselves are data points, and within those limits, the exploration continues. Telescopes push practical boundaries, revealing more of the accessible cosmos. Analysis extracts information from observations, constraining theories and testing models. The cosmic microwave background remains central to this enterprise. It is the anchor point, the most distant signal, the source of the most precise cosmological constraints. It defines the limit and provides the foundation. This dual role gives the cosmic microwave background its significance. It is both boundary and resource. It prevents observation of earlier epochs while providing enormous information about the epoch it represents. The answer to how far back telescopes can see is thus richer than a simple number. It involves understanding the cosmic microwave background, what it is, why it exists, what it reveals, and what it hides. Telescopes can see to 380,000 years after the beginning. They can see the cosmic microwave background. They can extract vast amounts of information from it, but they cannot see beyond it, into the hidden past it conceals. This is the structure of electromagnetic observation. This is the limit. This is how far back telescopes can really see. The answer points to a boundary. The boundary points to physics. The physics points to the evolution of the early universe. And the evolution explains why observation has the scope it does. Within that scope, the cosmos is available for study. Billions of years of history, billions of galaxies, the emergence of structure and complexity from primordial simplicity. All of this lies within the accessible region, bounded by the cosmic microwave background on one side and the present moment on the other. The present moment is where we observe from. The cosmic microwave background is as far back as we can see. Between them stretches the visible history of the universe, the record preserved in light that has traveled across space and time to reach our instruments. This record is what cosmology studies. This record is what telescopes reveal. This record is bounded, but it is vast, and it is ours to explore. The cosmic microwave background is where that record begins. It is the first entry, the oldest signal, the starting point. Before it, there is no record in light. After it, there is everything observable. This is the answer to the question. The cosmic microwave background, 380,000 years, the edge of the visible past. The light from that epoch still arrives, continuously, from every direction. It has been traveling since before any star existed. It will continue to arrive, cooling and stretching, for as long as there are observers to detect it. It is the oldest light in the universe. It is the limit of electromagnetic observation. It is the boundary of the visible past. It is where the question of how far back telescopes can see finds its answer.